Okay, hello everyone. So we are going to do a Q&A about the current state of Wolfram Physics Project. Maybe I can start by saying a few things about what's been going on. Things are chugging along just great. It's a complicated thing because physics is big and there are lots of things to do. More and more people getting involved. We have our collection of research affiliates and junior research affiliates, about 30-something people, all sort of connected directly to us and to the project, and people working on all kinds of different things. I would say there's a range of activities going on, from the pure exploration of the computational universe, kind of NKS type things, through to much more connected to direct experiments about physics kinds of things, and a lot of mathematical physics connections in between. So what's been, and I guess another thing that's going on is the use of the formalism that we've developed for the physics project for lots of other applications. And that's something I personally have ended up in a bit of a rabbit hole, studying things about meta-mathematics and so on, having realized that our formalism can be applied to those kinds of things. That might seem like kind of a waste of time for the physics project, but it isn't. The key point is that the idea of multi-way systems turns out to be a really general thing. And multi-way systems are a way of thinking about kind of systems that have many possible alternatives to what they do at each step. But they're a more global way to think about those things. And they're a way to think about those things that have concepts like causal graphs associated with them and so on, things which have not really been introduced in other places where there are like multiple choices of how things can go. And what I've been interested in particularly is trying to develop more intuition about this kind of new type of construct that we have, multi-way systems. Well, it's not really that new. I started talking specifically about multi-way systems in 1994. But it's a difficult concept, and it's something where there's a lot to understand about how to think about it intuitively. And I think it's really useful to think about multi-way systems in the context of mathematical theorem proving, in the context of games, in the context of number theoretic kinds of things, because each of these different ways of thinking about multi-way systems helps us get sort of closer in on, how to understand this concept. And for example, I've been interested recently in thinking about game trees, game graphs, tic-tac-toe, all the possible things that can happen in that, how that relates to the structure of multi-way systems as a way to get sort of intuition about things in quantum mechanics and so on that also work like multi-way systems. So that's for me been an important thing. Another big direction has been, as I said, the mathematical physics direction. And Jonathan Gorard and other people in our team particularly have been working a lot in that direction. And sort of the big news there is the connection of our formalism to things that are kind of at the frontiers of mathematical physics in various directions, in particular connections to the categorical description of quantum mechanics, and essentially part one of a multi-part series of papers with Jonathan as lead author just came out last week. It's already 100 pages of heavy category, higher category theory type stuff, basically proving the equivalence. It's one step in proving the equivalence of our formalism to categorical quantum mechanics, which in turn is known to be equivalent to standard sort of von Neumann formalized quantum mechanics, which is standard quantum mechanics. So that's an important step in kind of making all these connections between what we've been doing and what people have been thinking about in mathematical physics. And there are a bunch of other things along those lines that are being worked on. I have to say, I personally have also been thinking about, like last week, I think it was last week, put out a piece about understanding faster than light, going faster than light in our models, and the realization that in our models, because space doesn't have the kind of simple structure that one has assumed it had for a long time, in our models, the problem of going faster than light becomes sort of an engineering problem similar to sort of breaking second law of thermodynamics behavior, rather than a sort of pure physics problem. But again, exploring that idea led me to more intuition and more foundational notions about, for example, in that particular case, how space is reconstructed from causal graphs and so on. So an awful lot of kind of exploring the formalism and seeing it in other contexts, which I think is very helpful. I mean, I personally am about to launch into two efforts, three efforts actually, several efforts. One very practical, which is what are the phenomenological, the potential experimental consequences of our models that are, potentially immediately accessible. Now, many of those things, the actual parameters may be such that you can't, you can't see them easily. But the issue is, how do we at least even conceptualize what kind of thing could you measure? It'll be a lot of work to actually do the astrophysics, do the particle physics, whatever, to figure out, oh, you should see this particular value of this particular thing. But the first thing is just to surface what kinds of things might you be able to see. And we've done a few of those things in these working sessions, but that's another thing that I hope to pursue. Another thing that's also more on the intuitional side is one of the realizations of our project is there are different views of physics. That is, the physical laws that we humans, with our sensory inputs and so on, attribute to the universe aren't the only possible ones you could attribute to the universe. And again, as a matter of both intuition and sort of philosophical understanding, I've sort of launching into an effort to understand the broader picture of what are some radically different views of the universe that you could have while still describing the same underlying computational processes. Let's see, we already have a few questions here, but I'm happy to address lots of things. Calais says, I sent something to Jonathan about Susskind's recent work on information density. It seemed relevant. Jonathan, are you here? Do you want to comment on that?
Embarrassingly, I don't actually remember this particular email exchange if it happened. Susskind has done some stuff. I don't know about this particular comment, but Susskind has definitely done some stuff that we think is of relevance to the project, particularly around sort of a complexity theoretic view of the ER equals EPR conjecture. So there's this idea in sort of modern quantum gravity, which is the Einstein-Rosen equals Einstein-Podolsky-Rosen conjecture, which is hypothesizing a relationship between the if you have a pair of this is a loose explanation, but hopefully it will give you the intuition. If you have a pair of entangled black holes, then that pair of entangled black holes behaves a bit like a wormhole solution to the Einstein field equations, because essentially you can transmit information through one event horizon into the other event horizon through a quantum teleportation process. And that works a little bit like how you can go from one point in spacetime to a different point in spacetime by following an Einstein-Rosen bridge, a wormhole solution. And so the ER equals EPR conjecture, which comes out of ideas like holography, is this conjecture that actually these two things are ultimately equivalent, that there's some duality between entanglement and wormhole solutions, i.e. the large-scale geometry of spacetime. And in particular, Susskind and Doug Stanford and some other people have been responsible for formulating a complexity theoretic view of that, where the entanglement entropy of the two black holes, which is basically a measure of quantum computational complexity, is related to certain features of the classical bulk geometry of the associated wormhole. And that's a place in conventional quantum gravity where people are starting to use ideas from theoretical computer science, and where we think we have something to say about that, where effectively we have a way of reformulating that correspondence in terms of a complexity theoretic view of the multi-way causal graph. And we still don't know in complete detail how it's going to work out, or whether it's going to completely connect with things that people like Susskind have been doing. But that's definitely a kind of a correspondence that we think does exist. But I should look into.
Maybe you should say something about how, the basic idea is the multi-way causal graph is something which relates branchial space and physical space, which is essentially the story of holography, the story of ER equals EPR. And for us, that's something which just comes out because in the multi-way graph, there are branches. That branching process is what defines the different states of quantum mechanics and so on. And the connection between those states defines branchial space, which is sort of the space of quantum states. But there's also the idea of physical space, which is associated with, for individual states, what's the commonality of the hypergraph between those individual states. But the point is that in the multi-way causal graph, all these things are packaged together. And so this ER equals EPR thing can be thought of as different projections of the multi-way causal graph. At least that's the current, this is intuitively going to work out. It's going to be a lot of work for Jonathan and others to actually untangle the mathematics of what's going on. But that's the intuition of what's going on, I think.
Right. And we should also say that there's, in terms of the connection to computational complexity theory, so that's something which in the conventional way of formulating quantum, conventional ways of formulating quantum gravity is a somewhat unexpected counterintuitive connection that, that entanglement entropy, which is ultimately related to the computational complexity of a sort of quantum Fourier transform operation that you need in order to reconstruct information from the event horizon of a black hole. The fact that that should be connected to features of the bulk geometry of space-time is not at all obvious in the conventional way that physics is set up. But in our way of formulating things, it's much, much more intuitive, because both physical distance in physical space and distance in branchial space, as Stephen mentioned, are really complexity theoretic measures, in the sense that when you say these 2 points in the hypergraph are a certain distance apart, ultimately what you're saying is that if I wanted to propagate a signal from one to the other, there's a certain minimum number of rewrite steps I would need to, a number of rewrite rule applications I would need to do in order for that information to be successfully propagated. So geodesic distances in the hypergraph and in the causal graph are really statements about computational complexity of certain information propagation sort of processes. The same thing is true in the multi-way system as well, because when you say that there's a certain common ancestry distance between two states, you're really saying up to some factor of 2, there's a minimum number of rewrites I would need to apply in order to transform from one state to the other if I'm allowed to reverse some of those rewrites. And so the fact that both of these things should be connected to features of computational complexity theory makes total sense in this setup. And the fact that people seem to be rediscovering the same thing independently in these other completely different setups is, I think, a really, really positive sign.
Right. I mean, at this point, we're sort of checking off. There are these, what's known in mathematical physics, what's known in physics. In mathematical physics, there are various frameworks, and we are steadily checking off, how do they relate to what we're doing? Causal set theory. How is what we're doing generalizing causal set theory? How is what we're doing related to categorical quantum mechanics, etc.? We haven't done string theory yet. String theory remains out there, and somebody should really do it before we get to it. Eventually, we'll get to it, but I kind of was assuming somebody else was going to do that one. Because it's fairly clear how it's going to work, but and it's going to be quite interesting. It's going to give us a lot of intuition. See, one of the things that I think is really interesting about what's going on is, by having this framework, we have this kind of way of connecting together these things that have been intuitionally very different, which includes how to think about distributed computing versus how to think about physics and reference frames. That's an important connection, I think. That in distributed computing, we will be thinking about, programming in reference frames. We're importing kind of the intuition from physics to distributed computing and vice versa. And, it's those kinds of connections that I think are what will allow us to really make good progress, because in the end, it's really important to have these ways to think about things. There's one thing is the technical details of how you actually work something out. The other is, what is the context? What's the way of thinking about it? And that's an important part of what's developing. I think, there was some, so a bunch of questions here that, I was going to say one thing about black holes and other things. I mean, one thing that I have to say, I first wondered about when I was a quite young kid is, are particles actually just black holes? And we're getting closer and closer to that conclusion that, in some sense, particles like electrons and so on, which in our models are features of space, we imagine them to be some kind of topologically stable feature of space. But I think, the relationship between what's a black hole, what has an event horizon, what counts as a topological feature of space. I'm not sure, maybe Jonathan has some words of wisdom about that connection, but I think that there's an increasing it's increasingly looking as if the kind of lump of weird stuff in space versus black hole are at least a very similar story.
Right. I agree. That does seem like a plausible hypothesis. I mean, for me, the interesting question is, if it's the case that the description of a black hole singularity and the description of a topological obstruction that is an element that we interpret as an elementary particle, it could well be that those descriptions are actually very similar. But the interesting question, I guess, would be, in the elementary particle case, do they end up being naked singularities, or do they obey? Is there an event horizon of particles, and if so, what does that really mean? What are the sort of implications of that for things like particle interactions?
Well, I think yes, but my belief about that would be it's the same kind of no hair story as black holes. That is, the fact that all electrons appear to be the same might be the same reason that all Schwarzschild black holes appear to be the same. That is, that an electron, it could be the case that every electron might have its own personal story, but it's inside its event horizon. I mean, that's its own personal way to attach to the main part of the hypergraph, but it's inside its event horizon. And so, with respect to every external property of the electron, it has only a definite form. I think that's that's kind of the intuitive idea. But really, one of the things that I would say we've been remiss in doing, we haven't done yet, is really go on a hunt for particles. We've kind of been waiting. There are a few things that we're trying to do in preparation for the hunt for particles, which is the hunt for topologically stable structures in hypergraphs and so on. One is Max Piskanov's work on local multi-way systems, which has been going rather well, and where the idea is that you're able, so one of the things that I'm keen on is this concept of multi-space, this combination of physical space with branchial space, where what we've been doing so far is mostly talking about global multi-way systems. That is, this is the multi-way system where every node in the multi-way graph is a whole state of the universe. The idea of a local multi-way system is that you get to kind of weave together only those parts, the things that are sort of common to different states of the universe are all together, and it's only kind of bubbling out in the direction of things that are not common. And that's this concept of multi-space. And we've been trying to sort of start understanding multi-space. And it's just a very challenging thing to wrap one's head around or to visualize and so on. But that's one thing is the development of local multi-way systems. Another thing is that we've been interested in the origins of quantized spin for particles, and also the origin of fermions versus bosons. And we've made some progress. I think we have a good qualitative idea about how that works. And it's just a bunch of heavy lifting mathematical physics to really nail that down. And I think both Jonathan and I have been distracted by different kinds of particular projects. Arguably mine are well, I don't know whether mine are less relevant or more relevant, but they're different at least. And so we haven't really worked as hard on that issue as we might. I mean, to give you a qualitative idea, spin is quantized. We know that the electron has half h bar of spin, photon has 1 h bar of spin, etc. Why is it quantized? Why is angular momentum quantized? In our models, we have a picture of what angular momentum is. It is my strong guess that there is a story of homotopy in the multi-way causal graph that will end up being some homotopy group type thing in the multi-way causal graph will end up being the story of why there's quantized spin. We'll see. One of the important things about spin is there's half integer spin and there's integer spin. Half integer spin is associated with fermions, things with Fermi statistics. Integer spin associated with things with Bose statistics. Understanding that spin statistics connection and understanding even the idea of spinors, half integer spins, which are things where even if you rotate through 360 degrees, you don't come back to the same thing again, you come back to minus the same thing. Understanding that in our models. So our current suspicion is that spinors are, it's as simple as this. Spinors are associated with directed hypergraphs, and the ordinary rotation group, not the spin group, the ordinary rotation group, vector type things are associated with undirected, things which are effectively undirected hypergraphs. And they're kind of ways that one can model that involving taking limits of these kind of equivalence classes of regions in the hypergraph and looking at the limits of those equivalence classes and how they limit to things like Lie groups. And that's kind of a coming attraction that we haven't really done. And the whole question of Bose statistics versus Fermi statistics, whether particles like to get together or whether they like to stay apart. Our current guess is that that's associated with divergent paths in the multi-way graph and paths that converge in the multi-way graph. The convergent paths being the Bose-Einstein statistics, the non-convergent paths being the Fermi-Dirac statistics. That's at least the current thought about this. Jonathan, do you want to add something to that?
No, I think that's a pretty good explanation. So I mean, and as the one thing I think that's worth emphasizing there, which I think you kind of mentioned at the beginning, is that this is a way of thinking about Fermi-Dirac versus Bose-Einstein statistics as a bulk feature of the universe, right? Which is not conventionally how it's done.
I didn't mention that, and that is very important. Yeah, I mean this idea, this is the surprise, one of the many surprises of this project. Okay, the fundamental meta surprise of this project is it's been a lot easier than I expected. Now that's kind of one of these, you shouldn't say that because you don't know what's coming next. But the thing that's been easier about it is I thought we would have a much bigger hill to climb with computational irreducibility. We would be able to say less. The other thing I thought was that many phenomena that we would look at could not be found in idealizations. So what do I mean by that? I mean that to understand energy, we would have to understand what electrons are, and then we'd have to count electrons and look at the properties of electrons and so on to understand energy. But one of the surprises of before, end of last year, I think, was the realization that energy and momentum can be thought of as bulk properties of the spatial hypergraph, the causal graph, etc. And so is Fermi-Diracness, is the fact that things obey an an exclusion principle, is that a statement that can be made in bulk, or does that have to be made in particular, in a pun? I'm making a bit of a pun there because when I say in particular, I mean only with respect to particles, so to speak, because we don't yet know how particles work. And the interesting thing is it looks like we can make statements about statistics in bulk. Now, that's not super surprising, because after all, we do have bulk Bose-Einstein systems, and we have bulk Fermi-Dirac systems too. So it isn't, in quantum statistical mechanics, both of those things are absolutely things, so to speak. One of the connections here, which we haven't really explored, somebody looked at a little bit at the summer school, is back in the day, I had these simple cellular automaton models for the molecular dynamics of gases and so on, of fluids, where you just have a bunch of discrete cellular automata bits going around a bit like molecules, and then large scale limit, the thing behaves like a fluid with continuous velocity field and so on. Well, you can do the same kind of thing in a multi-way graph where the collisions in your cellular automaton aren't deterministic, but they have multiple possible outcomes. They're not a single way system where there's just a single history. There's one where there's a branching history. So that gives us, I think, a way to get from our models to quantum statistical mechanics. And quantum statistical mechanics has notions of kind of bulk Fermi-Dirac, bulk Bose-Einstein statistics. And so I think that's a possible way into an understanding of Fermi-Dirac statistics in bulk and so on. I mean, I would say in terms of these surprises, the fact that we can understand quantum phenomena, quantum mechanical phenomena, not using our full hypergraph formalism, but just using string rewrite systems is very interesting. It's not super surprising after the fact, but it makes it a hell of a lot easier to do these analyses, that we can actually analyze the double slit experiment, the quantum teleportation, these kinds of things in the context of these string rewrite systems without having to build this whole structure of space-time. And by the way, I should say that Jonathan wrote up a little bulletin about the double slit experiment, and which has been variously applauded and criticized for its apparent sleight of hand of, how do you actually get to this answer? And it turns out that we're increasingly understanding how one gets to that answer. And it's needless to say, it's a pretty subtle piece of mathematical physics. And the fact that it was possible to barrel through and get to that result as comparatively simply as in that bulletin is, it's interesting. And it's one of these things where it turned out to be easier than we thought. The real story has to do with how do you make coordinates in branchial space. In physical space, we have the notion of coordinates. There's, 3 dimensions of space and so on. In branchial space, formed from all these branches in the multi-way graph, how do you make coordinates out of those? That's hard to do. And one of the surprises, which seems to be being validated in multiple places, is that one common thing that happens, which is absolutely frigging bizarre, to me at least, is that there is a natural, let's say, 2-dimensional structure to a piece of the multi-way graph, but the actual coordinatization ends up being the result of a space-filling curve, a 1-dimensional space-filling curve, snaking its way through that naturally 2-dimensional structure, which is really bizarre. Not seen before, not the kind of thing one's seen in other kinds of physics, but that seems to be the way that sort of coordinatization in branchial space, one of the tricks of coordinatization in branchial space. Now, I think that the more official version of this is coming from Jonathan and Xerxes and Mano's work on categorical quantum mechanics, and that's a much heavier lifting process in mathematical physics to understand how that all works. Jonathan, any comments, any latest late breaking news about how that's working out?
Not any particular news in relation to that, but I should just say something about how that whole kind of correspondence is working. So so as Stephen mentioned, right? So there's this view that, which we get from this project, of quantum mechanics is kind of the idealization of what happens when you throw away the actual geometrical structure of the hypergraph and you only consider the combinatorial structure of the multi-way system. And conversely, kind of general relativity seems to be the idealization where you throw away the combinatorial structure of the multi-way system and you only care about the geometrical structure of the hypergraph. So there are other ways of formulating quantum mechanics that people have considered in terms of ultimately diagrammatic rewriting rules over combinatorial structures that produce multi-way system-like objects. And one of the most sort of famous ones is this thing called the ZX calculus that comes out of categorical quantum mechanics developed by Kocher and Duncan. And so the way that it works is you represent an arbitrary sort of linear map between qubits as this thing called a ZX diagram, which is ultimately just a directed graph with particular sort of tagging of the nodes. And then there's a rewriting language you can define over those graphs that's provably complete, consistent, and sound, in the sense that two linear maps in quantum mechanics are equivalent if and only if the 2 diagrams are mutually rewritable to one another. And so what we've been working on is basically trying to sort of represent that in this multi-way system framework and show that the multi-way system formalism is a kind of an abstract generalization of this idea. But one of the really nice features that we weren't really anticipating when we first started doing this, but it's kind of obvious in hindsight, is that these ZX diagrams basically have their branchial space already coordinatized, because every ZX diagram, the individual nodes, which are called spiders in the ZX diagrams, have phase information associated with them, and that phase information is one of the things that's manipulated by these rewrite rules. So given a particular diagram, and because branchial space is naturally laid out in terms of quantum phase, given a particular ZX diagram, we already know a priori what its coordinate is in branchial space. So in effect, so unlike in the hypergraph case where we're trying to kind of figure out what the answer is in relation to this coordinatization problem, the ZX case is really nice because we know what the answer is and we need to figure out why the answer ends up being what it is. And so it's in this particular instance that we've been able to show that the natural phase coordinatization of the branchial space of ZX diagrams happens to have this space-filling curve structure that ultimately turns out to be related to the fact that the individual, in their operator form, when you try and construct a composite phase for the overall ZX diagram, what you're essentially doing is you're applying a pairing function over the arguments in the individual, over the arguments of the individual operators for each spider. And the pairing function you're applying is some generalization of the Cantor pairing function that is known to produce space-filling curves. And so
this is going to submerge deep into this ocean of great complexity here.
Right.
This is hard to explain. I mean, yeah, I could try and do my version of what I think is going on there, but yeah, suffice it to say, you can look at Jonathan's paper if you're interested in knowing what the actual story is.
Right. But that's the basic picture of kind of what we figured out so far. And so we think that So one of the many reasons why I think this whole categorical quantum mechanics sort of side project is worth pursuing is because I think that ultimately it's going to allow us to prove, I think, quite a general coordinatization theorem about branchial space. It's going to allow us to kind of define a general procedure for, given a particular multi-way system, what is the procedure for assigning phase coordinates for each of the states? The ZX case gives you a particular instance of a multi-way system formalism, which you can do that. But we have reason to believe that actually those procedures can be generalized essentially to any multi-way system. And so that's a nice kind of spin out of that project that we hope will be coming quite soon.
By the way, I just want to mention methodologically, I keep on saying this project is going more easily than I expected. But part of the reason for that is that, we've got a stack of tools that we've been building for a really long time. Particularly I've been building for a really long time, that are what make this possible. And if we look at some of the things that are actually going on, so we're making increasing use of automated theorem proving, for instance, which is a fairly heavy lifting, symbolic methodology, which really has not been used that much for fresh research. I mean, I used it 20 years ago in finding this axiom system for Boolean algebra, but generally automated theorem proving is used sort of after the fact to fill things in. We're using it as much more of a primary, actually figure out what's going on type of approach. The other thing is being able to do serious computational experiments to both figure out what's true and develop intuition is really quite important. And for us, these seem like, oh, that's easy. Those have been, those are pretty much, blocking items in terms of that have, the good news is they seem easy to us, and that's why we're able to make progress here. But it's interesting methodologically that we're kind of taking for granted these things which are actually not common tools that end up getting used. And it's interesting to me that these tools end up being as valuable as they seem to be to us. All right, we have many, many questions here, so let me start addressing some of these. Okay, question here from Beauty. First question, could the cosmological constant be a rule instead of a number? Okay, so what is the cosmological constant? So that has to do with what space is. In our model, space is the result of these elements in this hypergraph being sort of knitted together by relations in the hypergraph, which are themselves defined by activity in the hypergraph. So a way to think about it is the reason why there's a thing like space that seems to be sort of coherent and where you seem to be able to sort of move in it is because all these sort of atoms of space have been knitted together by these update rules that connect different parts of space. So if everything just stopped, if the clock stopped, so to speak, there isn't a global clock, but if the process of computation, that is the rewriting of pieces of this hypergraph, if that stopped, space would effectively fall apart. There wouldn't be any sense in which you could say, oh, I'm moving from this part of space to another, because that process of motion involves basically the fact that the space that you're doing operations in space in order to achieve that motion. So in a sense, space is a thing knitted together by the continual activity in the universe, and the structure of space is defined by that activity. And the question of a cosmological constant has to do with what is the effective energy density of that space. And that in turn has to do with, in our model, we actually think we know what energy density is, and it has to do with essentially directly activity in the amount of activity in this hypergraph. And it's hard to define all this stuff because it's like, it's activity in space, but then you're talking about the density and amount of energy per unit volume of space, but you don't have a notion of volume because that's defined by the structure of space, et cetera, et cetera, et cetera. So it's all a bit trickier and a bit slipperier. But the end result is, what's happening in the universe is most of what happens in the universe is the maintenance of space. Most of what happens in the universe is the knitting together of these atoms of space by these continual rewrite rules. And in fact, perhaps in our estimates of magnitudes of things, all but 1 part in 10 to the 120th of what's going on in the universe is the knitting together of space. And everything that we know and care about in the universe is just that little froth, that 10 to the minus 120th piece on top of the major activity of the universe, which is the knitting together of space. Okay, so having said that, the cosmological constant has to do with what is the zero of energy for space. And is the zero of energy, there's all this activity going on in space, which is what knits together space, but activity is also what produces energy. So energy, what you attribute to being energy in a particular part of the universe is the difference between the amount of activity going on in that part of the universe and the typical amount of activity going on in the universe. So in a sense, the cosmological constant is a story of what do you count as the zero of energy. And the question of whether you can have, for example, changes in the cosmological constant, things like this, over the course of time, whether different parts of the universe can have different effective cosmological constants, those are all questions about is the structure of the spatial hypergraph, how uniform is it? One of my kind of weird things is the notion of vacuum cleaners, which are regions of the spatial hypergraph which have less activity than the typical. Those regions will behave as if they have negative energy density. From the point of view of gravity, they will behave as if they're like dark energy. They're like something that leads to a repulsive force of gravity, a negative mass force of gravity. But so that's but one thing we'd love to be able to calculate is what the cosmological constant is. That will be a really cool thing to be able to calculate. Another thing we wonder about is, how does the cosmological constant play out in branchial space instead of physical space? Not clear. How does the expansion of the universe play out in branchial space? Not clear. These are all questions that we're still having to investigate. I would say one thing about the cosmological constant that I actually think is fairly near at hand is this phenomenon called the Casimir effect. Casimir effect is a phenomenon of quantum field theory. So in ordinary quantum field theory, one feature is that every quantum field, whether it's an electron field, a photon field, whatever other field it is, you think about that field as being a sum of pieces that correspond to sine waves of different frequencies. They're the modes of the field. A free field has modes that are just like sine x, sine 2x, sine 3x, sine 4x, sine 5x, etc. And in the vacuum, in standard quantum field theory, there's half a unit of excitation of every one of those modes. So it's as if in the vacuum, it's sine x plus sine 2x plus sine 3x plus sine 4x. That represents, in a sense, the activity of a quantum field. There isn't the vacuum, even in ordinary quantum field theory, is not a place where nothing happens. It's a place where every mode, there's a bit of every mode of the quantum field that exists. But you say, but that doesn't matter because it exists everywhere. So when we say what exists somewhere, we're saying what exists here that isn't something that exists everywhere. What's the difference between what exists in the formal language of quantum field theory? It's called normal ordering. Is the way that's a trick for basically zeroing out those all of those kind of activities from 0 point fluctuations in these quantum fields. Okay, so having said that, if you were to make a box that had metal plates, for example, just two plates, big plates, and you were to say, okay, I want to look at the modes of the field between these plates and the modes of the field outside the plates. The point is that between the plates, any mode of the field that has a wavelength that's longer than the distance between the plates can't exist between these plates, but it can exist outside the plates. And so that leads to this strange phenomenon called the Casimir effect, which is a phenomenon where basically there's a force that comes because all these modes on the outside exist, but they don't all exist on the inside. And so there's sort of a pressure from these fluctuations in the quantum field from the outside pushing in on these plates. And it's an experimentally measured thing that happens. I mean, I should say that it's not actually as obscure as I'm making it sound, because actually van der Waals forces that are very relevant to holding lots of molecules together and so on, are forces between molecules and so on. Those are related to exactly the same phenomenon there, but they happen to operate in the vacuum fluctuations operating on the inducing electric dipole moments in the distribution of electrons and so on. And it's in fact the same kind of phenomenon. But in any case, this Casimir effect, in our models, we should be able to compute the Casimir effect. We should be able to compute gravitational generalizations of the Casimir effect. The Casimir effect in the interior of a black hole is something we should be able to start computing. And I think that may give us some insight about the cosmological constant and the way in which we can sort of bulk properties of the vacuum that we can make measurements on. Let's see. Tarka is asking, what's the current understanding of the standard model of particle physics using our model? Well, oh gosh. Okay, the standard model of particle physics has three basic elements: a certain set of particles, quarks and leptons and things like that, a certain set of gauge fields, and the Higgs sector. Okay, those are three sort of pieces of the standard model. Let's talk about each of them. Actually, the one perhaps to talk about first is the gauge component, the gauge bosons, the photon, the W and Z bosons, the gluons. These are associated with, these are the carriers of forces. They are associated with local gauge invariance. Okay, we have been a bit remiss, I would say, in the last few weeks in investigating local gauge invariance. We had a really good lead on local gauge invariance. We think we understand basically how local gauge invariance works in our models, but we have not explored it, and we need to explore it. Somebody, maybe Jonathan, can comment on the state of local gauge invariance. I know Graham was studying this, but I haven't heard what he's been up to for the last few weeks, so we don't have a current. I don't have a current status on this. But the sort of the bigger story is, can we reproduce these sort of local invariances in our models, and can we understand the gauge groups that occur in the standard model? Do you want to comment on, Jonathan? You looked like you were going to.
Yeah, sure. So I can give some quick explanation of how sort of fiber bundles local gauge invariance kind of works in a discrete setup, or at least a conjectural formalism of how it can work. So one thing you can do is you can start from a total space that is discrete. So you just start from some set of discrete points, you call it a total space, and then you define a discrete gauge group over it, like, you know, the icosahedral group, I think, is Stephen's personal favorite example. And then so you look at then the group action on that space, and in particular you look at the orbits of each point, right? So that because of
Jonathan, if we're going to explain this to people, we have to go much lower. Let me try a version of this, okay? So first thing is, if you're thinking about an electromagnetic field, like an electric field in space, how do you think about that? The answer is, at every point in space, there is a value of the electric field that is defined by a vector, which has some direction. That direction is a direction that is not a direction it is a vector that points in a direction in space, but it is not a vector that you can think of as being in space. It's something where at every point in space there's a vector sort of attached to that point. Or in general with electromagnetism, I'm kind of cheating for electromagnetism actually, because in electromagnetism the real story is there's this phase associated with a U1 gauge group. There's this like, where are you on a circle? But that circle is not something laid out in physical space. That circle is in the space of the gauge group. But there's a version of that circle, there's a copy of that circle associated with every point in physical space. And the mathematical structure that one says one has is a fiber bundle, where this gauge group, the degrees of freedom associated with the electromagnetic potential are the things that exist in the fiber. And there are fibers, it's like a carpet or something, where there's a fiber at every point on the carpet, so to speak. The base space is physical space, and there's a fiber that represents this internal, what can exist internally. And it's the internal degrees of freedom, the internal sort of motion within the fiber that's associated with the gauge group. Okay, now that I tried, perhaps unsuccessfully, to explain what a fiber bundle is, you can now go back to, you were talking about this
sure, I mean,
version. Go ahead.
Yeah, right. Okay, so the really nice thing is that the continuous setup that Stephen has described, which is the standard sort of way of thinking about gauge theory, has quite a nice discrete extension. So in this case, the total space that you start from is now a discrete set of points, and the gauge group is no longer a Lie group; it's some discrete group, like the icosahedral group, which is some approximation to a rotation group. And so what happens is that there's this theorem, Cayley's theorem, that says anytime you have a discrete finite group, it can be thought of as being basically a permutation. Its action can be thought of as being a permutation. So when you define this discrete gauge group over your total space, what it's doing is it's just taking the points in that space and permuting them, relabeling them. And so what you can do is look at and because the space is finite, there's only a finite number of points. there will be a finite orbit. So, you know, point A will be relabeled to point B will be relabeled to point C, and so on. And eventually you'll get back to point A. And so what you can look at are the orbits of each point in the total space under the action of this gauge group. And those orbits form loops in this other combinatorial structure. And each loop we refer to as being the discrete analog of a fiber. And therefore the overall combinatorial structure that contains all of the loops, all of these orbits, is the fiber bundle. And so one of the really nice things about that is that it preserves all of the standard kind of algebraic and geometrical features of gauge groups and fiber bundles in the continuous case. So for instance, it's known that if you take a fiber bundle, you mod out by the group action, then you get back to the base space. And that's exactly what happens here. And in the same way, there's this notion of a connection that exists in gauge theory, which is a rule that says if I make an infinitesimal step in the base space, that should be lifted to some infinitesimal step in the fiber bundle. And the connection is the rule that allows you to do that lifting. And here, again, there's a very, very direct, discrete analog of it, which says if I have an individual edge in my base space, I can lift that to an elementary edge in the associated fiber bundle. And we have rules for doing that. So Graham, during the course of the summer school, constructed a kind of minimal example of this for a particular Hopf vibration, a particular sort of topologically non-trivial version of one of these fiber bundles for a non-trivial gauge group. And it seems to be correct. You know, there seems to be a legitimate way of doing things. And the reason why this gets really interesting is because local gauge invariance, the statement that your spaces are so for each fiber, there's a kind of collection of possible coordinate bases that you can pick. And local gauge invariance is the statement that kind of ultimately the structures of your spaces don't depend on which coordinate basis you choose for each fiber. So in our case, each coordinate basis, because of the way the connection works, each coordinate basis is associated with a particular hyperedge, which is in the hypergraph that's our base space. And each hyperedge is in turn associated with a particular orientation of your rewrite rules. And so local gauge invariance reduces to the statement that the structure of a space, like a causal network, is independent of the orientations in which you apply your replacement operations, and therefore is directly related to causal invariance. It's kind of it's a weaker version of causal invariance. And so
that's a nice version of that argument, Jonathan. That's cleaner than I've seen before. Okay, good. Yeah.
Thank you. Well, yeah, so we're making gradual progress towards kind of conceptually understanding what's going on. But yeah, what we need is a kind of complete mathematical theory that allows you to map concepts in continuous gauge theory to concepts in this discrete setup. And we have particular cases. We don't yet have the general.
You know, we should do one of these working sessions looking at local gauge invariance, because I think we should construct some more. We should just have a kind of production line of examples of. I mean, you know, we have this one example of the Hopf vibration, but we should have a production line of examples of these, because I think that will give us more intuition. I mean, we're going against, you know, Alan Turing wrote a paper about approximations to Lie groups, continuous groups, finite approximations to continuous groups, in which he basically concluded there isn't a way to do it. You're out of luck. There aren't finite approximations to Lie groups. I think for once, we're about to prove that Alan Turing was wrong about something. You know, because we have what amounts to a way of approximating Lie groups using, although he was considering the case of just a Lie group is sitting there, we're considering this case where there's fiber bundles and connections and so on, which is arguably a more complicated case, but probably has a limit that gives you the original Lie group thing. I mean, but by the way, I mean, the general idea, you know, Lie groups are sort of they are continuous groups, like the rotation group in 3 dimensions is a Lie group, which has where you can rotate just an infinitesimal amount, as opposed to the group of the icosahedron. Look at this. I'm actually going to be able to demonstrate this. Look at that. There's an actual icosahedron. What do you know? The whole point is that with the icosahedral group, there are only particular discrete transformations that will map this icosahedron to another precise icosahedron that don't just end up in a different configuration, but they're ones that end up with just, oh, that's just another, you know, it's just the icosahedron again. And that difference between the question of the continuous group where you can have infinitesimal changes versus just the discrete group where you have discrete jumps, like you might have for a square or something like this, how that limiting process works is interesting. What is, I think, an interesting analog is that what we've looked at in the spatial hypergraph, where we just look at when you have this graph and you look at a large enough version of the graph with enough nodes, you can think of that like a continuous space. So similarly here, this is like a large enough bag of discrete permutations can be thought of as a Lie group. And that's the thing, I explored that a little bit in the stuff we wrote, I wrote just before we launched the project, but we need to explore that some more. Okay, the third part of this would be the Higgs sector, the way that you give mass to particles. I don't think we have anything profound to say about that yet, other than that the notion of things like spontaneous symmetry breaking is closely related, I suspect, to features of the way that space is knitted together in our models, but the details of how that works we do not yet know. Okay, it's a question here. Digging deeper into alien intelligences in the sense of different worldviews, different perception systems, could it be parallel to the fact that artificial neural nets have a large number of minima? Skeptical, but possible. Let me explain what I mean. How do we think about the universe? Well, one thing we think about is we think about space and time. We think about the notion that there is a definite, that things happen at a particular moment in time. That is, that we look around and we say, the tree is moving, the this is doing that at this moment in time. But in fact, things at different places in space, the fact that we view things at different places in space as all happening at a single moment in time is a feature of our way of perceiving the universe. It's a feature of the fact the speed of light is fast compared to our brain processing speed, at least for the distance scales that we're dealing with. It's related to other features of the way that we perceive the universe. We might not perceive the universe that way. It might be the case that every separate event that happens in the universe, that happens at a different space-time point in the universe, was something separate, that we don't bucket it together as these big slices of space at a particular time and so on. That's an example of a difference. I mean, another big difference is this notion of what we say, oh, we can just think of water as a continuous fluid where all the parts of the water, of the little thing of water or something, every sort of point in this water is sort of the same, except maybe it has a different velocity of the water or something like that. But in actuality, there's individual molecules bouncing around there, and the particular detailed configurations of those molecules are completely different in particular places in the water. But in our view of physics, we just say, oh, it's just a continuous fluid where it has the same property at different places, and we don't consider all those discrete molecular motions. So a question that one might ask, I think you're asking, is an interesting question. If we're using neural nets as a way of understanding what's going on in the world, do they reproduce? Do they have the same prejudices that we have? Do they also bucket space in the way that we bucket space and so on? Would they also take all those discrete molecular dynamics and say, oh, it's like a continuous fluid? Okay, here's the situation, I think. The answer is probably they don't have to. The fact is that what we have done when we have neural nets and we train them, we are training them to connect what they do to our version of how we perceive reality. That is, we train an image identifier to say, that's a picture of a cat, that's a picture of a dog, not training it to say that particular pattern of fur on this thing is a this, and I don't care whether it's on a cat or a dog. All I care about is that particular weird pattern of fur or something. And so I think that what we have done to date with our artificial neural nets is very much we train them to connect to our view of how the universe works. Now, could they connect to a different view of how the universe works? To some extent, I think the answer is yes. I think that they already have certain prejudices built into them, because I think that they already have certain assumptions about continuity and calculus and so on built in, which are particular to our way of viewing the universe and might not be general to any possible way of viewing the universe. But I suspect that their views of the universe are more general than the ones that we humans have so far constructed. But as I say, when we actually use artificial neural nets, we're always training the neural nets to be doing things which are useful for us, which means they have to relate to concepts that we have, like cats and dogs and so on. But that's an interesting question. Let's see, question from James here. Have you considered that the events and branching could be converging rather than diverging? Actually, in our models, the whole point of this phenomenon of causal invariance is that every time there's a branch in the multi-way graph, there will eventually be a merge in the multi-way graph as well. And that's critical because it means that there is some invariance about history. That is, it doesn't matter, you couldn't just say, oh, we went on the wrong branch. All is lost. The world will never be the same again. The answer is the world will always be the same again because of causal invariance, because there is always a merge in the future. Okay, questions here that have come in from our site. Let's see, a question from Daniel. Has the number of abstract elements in the universe been constant since the Big Bang, or are they created and destroyed? Strongly suspect that the number has not been constant. We don't know that for sure, but we strongly suspect that the universe is expanding in branchial space, in the spatial hypergraph, in all senses. The universe is expanding, as in it's getting more elements, more atoms of space in the universe. We haven't proved that, but that's what we suspect is going on. The question here is the expansion of the universe associated with more abstract elements coming into existence? But basically, yes, we think that's what's going on. It's a little bit of a, I hesitate slightly because it's a little bit of a more complicated story, because what matters is things about the causal graph, and that has to do with events that happen in the universe. And the question of the trade-off between the number of events and the number of elements is a little complicated. But I think the basic bottom line is, yes, space is expanding because there are more atoms of space, basically. Let's see, there's a question here from John. Is it a crazy idea given the success of Lagrangian approaches to physical theories? What about methods that generate models that are not self-adjoint? Some models might explain things like dark energy being contained in invariant spaces, those with generalized eigenvectors and nilpotent operators. So I think, it's a bit of a tricky story, because non-self-adjointness, there's a question of unitarity, probability conservation. There's a question of time reversal symmetry, those are different questions. Time reversal symmetry isn't in fact true for the physical universe, and it's probably not what we're talking about. The main thing about self-adjointness of operators has to do with what amounts to probability conservation, that the sum of all probabilities has to be 1. And I think that's a matter of definition. I mean, in our models, we have this sort of counting of path weights in the multi-way graph, and that counting of path weights gives you just integers. But when you say, well, what's the probability of something happening, you're normalizing it across all the path weights in a particular slice of this multi-way graph that you're taking. Jonathan, do you have a crisper version of this?
No, so I think that's a pretty good explanation for what's going on in our models. But I think it's also worth bearing in mind that we don't even know whether hermeticity is true, even in the conventional way of formulating quantum mechanics. So there's this whole field of what's called PT symmetric, parity time symmetric QM, or non-Hermitian QM, that was largely sort of pioneered by people like Carl Bender, which comes from the realization that, to guarantee parity and time symmetry, your Hamiltonians don't actually need to be Hermitian. They just need to have they need to have entirely real spectra. And hermeticity is a sufficient condition for that, but it's not a necessary one. And so you can actually have these non-Hermitian parity time symmetric Hamiltonians, which violate algebraic unitarity. And so on the surface might appear to be incompatible with quantum mechanics, but actually from a physical standpoint, they are still sort of pseudo-unitary in the sense that they still allow, given an evolved quantum state, ket psi t for some positive t, you can always reconstruct ket psi 0. Which is kind of ultimately the thing that matters. That's why probability conservation of things are so important. They're measure preserving statements about your Hilbert space that mean you can always reconstruct the initial state. And so even in the ordinary mathematical setup of quantum mechanics, it's possible to make a perfectly sensible theory where your Hamiltonians are not self-adjoint and your operators are not strictly unitary, and still everything kind of works. And probably what's happening here is similar, that our model, there's no reason to believe that the operators that we're dealing with in the context of these multi-way systems satisfy exact algebraic hermiticity and unitarity. But what they do satisfy, as Stephen said, more or less axiomatically, are these key measure preserving properties, which are basically properties about conservation of path weights in the multi-way evolution graph. And in terms of reproducing the predictions of quantum mechanics, that's really all that matters.
Let me ask a question. I don't know. I mean, in the interaction between general relativity and quantum mechanics in the past, there were questions, as I recall, about hermiticity in that case too, but I suspect that's just a big mess of what it means to have, you know, what the simultaneity surfaces are and what time is, and probability conservation associated with different foliations of space-time and so on. So probably that's not that interesting for us. But am I correct in remembering that there was a big muddle with quantum mechanics in general relativity as well? Yes,
there is that confusion, and actually, in a way, it's a confusion that we implicitly face too. It's the fact that this story about foliations and reference frames does not play well with the standard mathematical setup of quantum mechanics is basically what you're referring to. The fact that which Hilbert space of quantum states you see is dependent on your reference frame, but all of those Hilbert spaces should be measure preserving. That places kind of unreasonably strong restrictions that don't actually seem to be correct. And so the basic reason why that's happening is because the mathematical setup, the basic problem from my perspective is that there isn't an analog of a Lorentzian manifold for quantum mechanics. So Lorentzian manifolds are lovely in relativity because because any individual slice through an anti-chain of that through an anti-chain of the causal partial order for that Lorentzian manifold will give you a particular Riemannian manifold, which is a particular version of space, and the Lorentzian manifold itself is a version of space-time. But in quantum mechanics, you kind of just have your Hilbert space, and that's an instantaneous thing. And this notion of a time-extended version of a Hilbert space that you can sort of foliate in these different ways, that's not something that people have really explored. And yes, so as Stephen, as you mentioned, people had tried to develop geometrical structures based on antisymmetric metrics and these weird non-Hermitian operators that tried to get some distance towards formulating that in the ordinary setup, but didn't quite succeed.
You know, that's an interesting point that you make. The Hilbert space is the basically spatial slice of the time evolution, which we have in the multi-way graph. And so what we should be able to have is a generalization of Hilbert space. Just as Lorentzian manifolds generalize Euclidean manifolds, we should be able to have a generalization of Hilbert space that is essentially a time generalization of Hilbert space. Yeah,
exactly, right. So in the way that we think this kind of works, and well, we have proof that it works, at least in certain cases, the individual branchial graphs that you see, which are the instantaneous time slices, act like the instantaneous Hilbert spaces from ordinary quantum mechanics. So the overall multi-way evolution graph is this time-extended version. It's like, as you mentioned, it's like the Lorentzian manifold analog of a Hilbert space.
Okay, so what's the analogy between that and twistor spaces?
Yeah, so that's where it gets kind of interesting. I mean, we don't know, but one of the features of the correspondence spaces that you get in twistor theory is that there are, from a particular twistor correspondence space, there's a fibration that gives you basically a projective Hilbert space, and there's a different fibration that gives you essentially a complexified Minkowski space. And so we think, although it hasn't yet been made very concrete, that has something to do with the fact that if you take one of our multi-way causal graphs, there's a projection that will give you space-time, a particular space-time causal graph, and there's a projection that will give you the multi-way evolution graph, which is, as I say, like this time-extended version of projective Hilbert space.
Okay, so are there discrete approximations to the twistor spaces?
That's a good question. I genuinely don't know.
I haven't seen one, but that doesn't mean
it would surprise me if there have been. It seems like something we would have found, but I am not aware.
Well, so the question really for us is, can we construct something? Can we look at our multi-way graph, a multi-way causal graph, and look at a limiting case of that? And just as there are tests that we can apply for whether our thing behaves like Euclidean space in d dimensions, can we, or Minkowski space in d+1 dimensions or whatever, can we similarly apply some aggregate tests to our multi-way causal graph and see whether it behaves like twistor space? So in other words, what is the analog? Like dimension, for example, is a thing that we can do to sort of measure, are we like Euclidean space? What's the analogous thing for a twistor space? There must be some. Go ahead.
We can do the same thing, just with the dimension being complexified. right?
Well, but complexification is a mess. I mean, we don't want complex coordinates particularly, but we can probably turn those into some other kind of coordinates.
Right. No, but the key thing, I mean, the thing that's nice about complex coordinates is kind of from a geometrical point of view, we know how they should work, right? Because in standard, CP4 or PT2 twistor space, you have 4 complex coordinates, and we know that geometrically those will behave like 8 real coordinates, but with a slightly funky multiplication property. And that's something that we should be able to test just using
we should just go look for it. If we didn't have all these questions on our live stream right now, we could go look at it right now. But yeah, it's something we should definitely look at, because we can generate, I mean, multi-way causal graphs are not your most simple-minded creatures, but probably, well, the question is, are we going to be able to get anything? We're going to need to do them from hypergraphs. We're not going to be able to do them from strings. Do you agree? I think the only way we're going to get what's that?
I agree, because you need higher dimensional objects. A one-dimensional space is not going to do it.
Right. So it's going to have to be a genuine multi-way causal graph. Those things are pretty complicated creatures. I mean, even our minimal examples of them are pretty complicated. But that doesn't mean we can't look at them. And then the question is, what we need is the test for these, the complex coordinates test. The test for, do we have 2n complex coordinates? And that should be, we should be able to measure, just like we can measure a ball. Okay, so what happens to a geodesic ball in that situation? Can you talk about a property of a geodesic ball when there are 2n complex coordinates?
Yes, you can. So presumably you mean n complex coordinates, and
n complex coordinates, 2n.
It will behave like it will behave a bit like a geodesic ball in a 2n real coordinate space, but there will be an additional, basically something that acts like a contraction map that results from complex multiplication. I don't know offhand exactly how that formula works, but I know that there is one. There is a sort of a direct analog of that.
So in other words, when we look at the volume of that ball, we'll be able to see various kinds of, or actually we'll probably have certain symmetries of that ball that are associated with the fact that these are supposed to be complex variables.
Exactly. There's an additional symmetry that wouldn't exist in the 2n real dimensional space because of the fact that certain multiplications of complex numbers are equivalent. That there's a spherical symmetry that's imposed by complex multiplication that you have to take into account.
Okay, I bet we can find that. I bet that will end up being a property that is an inevitable property of the multi-way causal graph, possibly because of causal invariance. I'm not sure.
Right.
That there'll be, or even it may be more structural, more kinematic than causal invariance. That there's an inevitable feature of the very construction of a causal graph that leads to that kind of thing.
Right.
All right, let's go. We should go find that. Okay.
By the way, I should just quickly mention that there's a thing I've just been working on very recently, as in like today, that's related to this in the sense that it's okay. So this geodesic ball way of measuring volume is a very it's a nice, robust way of measuring volume, but therefore of inferring the dimension of a particular causal network. Or in the causal network case, it's not a ball, but it's a cone, but the same basic idea. But there are many sort of alternative methods that people have kind of proposed for doing this in the discrete setup, and they have different properties that are sort of characteristic of the methodology. And one of these is this thing called the Mearheim-Meyer dimension estimate, which gives you in the real case will give you the same sort of dimension estimate as the geodesic ball volume thing. But in the complex case, it will actually give you a different answer, and that's an instance of something of a test we can potentially apply in order to.
Yeah.
So actually, if I can just quickly share screen, I can show you very quickly how that works, and then we can move on to something else. But basically, what's happening is so here are some causal networks that I've constructed so that they are explicitly kind of faithfully embeddable into Minkowski space. So this is a 2+1 dimensional Minkowski space that's been represented using a transitively reduced causal network. And then, so what we're basically doing is you're asking the question: if we pick 2 events at random, what is the probability that they are related by the causal partial order? In other words, what is the probability that there exists a directed path from one to the other in the causal graph? And of course, that's essentially the question of, if we sampled points randomly in a space-time, what's the probability that they would be non-space-like separated? And that turns out to be a function of the dimension. And if we solve this somewhat somewhat complicated equation using n minimize, we can compute. So this is telling us that this is, given just 100 points, this is estimating the dimension to be approximately 3, to be 2.75. We know in reality it should be approximately 3. And you get, so you see, I think in this case, a quadratic convergence to the actual dimension. And so this is a
it's 3 because you sampled those points at random, like in a causal set type thing. You sample them in 3-dimensional space.
Exactly. So this is a 2 + 1 dimensional Minkowski space, which I've uniformly sampled using a Poisson process. And therefore it's nice because you can prove that the resulting causal network is faithfully embeddable into that space. So this is a radically different way of doing dimension estimation. There are some others that I've implemented, like the midpoint scaling test and other things. Each one has its own kind of set of features and pathologies. And the interesting thing is that all of them behave slightly differently when you go to these weirder spaces, like complex, ones that involve complex coordinates. And so that's something we can start to use to distinguish between twistor spaces versus just ordinary spacetimes.
Yeah, it's really interesting. I think that the yeah, pity you weren't using 12.2 though, or maybe you were, because it now has spatial statistics capabilities, and you could actually do a Poisson point process directly.
Oh, I was using 12.2, but I didn't know that was a feature.
Yeah, there's a whole section of spatial statistics, although it's definitely Euclidean spatial statistics. Well, it's not Euclidean space because you can do it on the surface of the Earth as well, but it's basically it's manifold type stuff.
Cool.
Okay. Well, let's see. Let's keep going here. Robert is asking, what's been the biggest surprise since the project started? The biggest surprise has been a heck of a lot easier than I expected. I mean, I really didn't think we'd get anything like as far as we've got. As I say, these idealizations that keep on working, even though I thought we were going to have to, advance to another level of sophistication. It turns out, 20th century physics was, managed to figure out these places where you can successfully sort of make statements, even in the face of all this computational irreducibility and so on. I would say it's interesting, sort of, we're seeing, the other big surprise, I suppose, since the beginning of the project is the connection to these other areas of mathematical physics. The fact that the things we're doing seem to sort of form a Rosetta Stone for all these different approaches to mathematical physics that I thought were just completely separate kinds of things. And the other surprise is that this formalism is ending up being related to all these other areas that, look, basically the story is this. Cellular automata are the minimal approximation to parallel computation, where you know the structure of space and time. And they have many, many uses, many more than one could ever have imagined. This is the absolutely minimal model where you don't have any space and time, and where you have kind of arbitrary relationships between events, where you just have events happening that have arbitrary connections between them. And needless to say, I mean, like, for example, Max had just generated here, I'll show it. Let's see if I can pull it up. Let's see if I can get one of these. Okay, you'll see it here. Hopefully, let me just see if I can pull this into something. Humph. Let's see if I can get this. How do I get this to be? Oh, here we go. Yeah, I can show this. Let me share something here. Okay, this is courtesy of Max, very recent. So this is the beginning of being able to animate the behavior of one of our rules, showing progressive updates and trying to keep kind of the structure of the hypergraph. I mean, more or less, I mean, all that wiggling around, that doesn't happen in the real universe. All that happens in the universe is just the connectivity of this. But this is kind of showing sort of what happens in this model, and can see things going on here. Okay, so, I looked at this yesterday and I'm like, oh my gosh, our model is actually going to be good for embryogenesis as well, because there's exactly the type of thing you see happening, and the minimal models for embryogenesis are a bit complicated. And people have tried to use cellular automata at certain stages where you have a real sheet of tissue that exists. Then you can use cellular automata. But when you don't have the structure, where the spatial structure is still not defined, you can't. But this is a place where we absolutely have. It's like these little updates are just like the mitosis of cells and so on. And I suspect one's going to be able to make a model for embryogenesis this way, which is, again, just like a completely bizarre thing that wasn't at all expected. But that's a feature of having developed what ends up being a pretty general model for things. There's a question here. Does the theory have testable outcomes? Which prediction is most likely to be discovered first? It has all kinds of outcomes that are both theoretical predictions and experimental predictions. The job of figuring out, what the experimental implications are is pretty hard. It's always hard for any serious theory. That's hard. Which one will come first? I'm kind of guessing some of the cosmological ones will come first, and not the quantum computing ones and so on. But I might be wrong. It really depends on. There's one scale we need to know, which is the maximum entanglement speed, which is the analog of the speed of light in branchial space, and we don't know that value. If we knew that value, we will be able to make all kinds of very quantitative predictions. But so, for example, a typical example is the expectation from these models that there have been dimension fluctuations in the history of the universe. Now, when those occurred and how big they were and so on, we don't know. But just looking for dimension fluctuations that might have existed after the formation of the cosmic microwave background, that's an example of a type of thing to look for. If we find them, something really weird is going on that strongly suggests a model that our model has to be right. But then, can we get a quantitative version of that? Not clear. We can know things about polarization of photons coming from the cosmic microwave background that will have been different if they had different numbers of polarization states, if they traverse a region of space which has different effective dimension, those kinds of things. There are also possibly some predictions, and Jonathan, we haven't looked at these recently much, the things about photon correlations for photons in orbit around black holes. That's one that I think is quite promising, where it's kind of ironic that Einstein, for general relativity, had the prediction that the bending of light around the sun would be exactly twice what was predicted in the Newtonian case. And he was very lucky that was a scale invariant prediction. It was just a factor of 2. Other things that he might have tried to predict would have involved knowing the value of the cosmological constant, these kinds of things, which he didn't know. And so those wouldn't have been things that were predictable. But he lucked out in that he had one prediction. We had one qualitative predictions like the existence of black holes, although that wasn't understood for nearly 50 years. There are qualitative predictions like there could exist singularities in space-time. We have qualitative predictions like that as well, like this dimension change thing and so on, and a whole boatload of other ones. But in terms of quantitative ones, he lucked out in the scale invariant one. I think we might have a scale invariant one that is bizarrely similar, which has to do with photons in orbit around black holes, and the question of what correlations exist between multiple photons in orbit around black holes, and whether the correlation between, which is a sort of a story of the relationship between physical space and branchial space. And I actually haven't thought about this for a couple of months, and we really need to work on it. We don't know, so my guess is that the first there will be suggestions. Oh, you should look for this, and those suggestions, some of those may pan out probably in the cosmological domain first. Then there will be this particular value of this thing will probably come later, unless we luck out in some scale invariant predictions. Eventually, when we start looking at particles, maybe we'll get predictions about well, we should get predictions about particle masses and all the rest of those kinds of things, but that might be pretty heavy lifting. It might require computations. I mean, as I say, so far we've lucked out. The things have been easier than I expected. That one, we'll see. We'll see. Maybe we'll be able to get particle mass predictions without doing sort of full heavy lifting of working through sort of computational reducibility. And in fact, this idea of correspondence between particles and black holes suggests there might be some sort of universal statements to be made there, just as there are universal statements to be made about properties of black holes and singularity theorems and so on. Has the question of preservation of information maintained during the evaporation of black holes been addressed? Yes, we think we do understand that. We think that the information paradox for black holes, which is the statement that quantum mechanics sort of preserves information, yet in a black hole, things just sort of fall into the black hole and disappear in the singularity or disappear behind the event horizon. That, you know, how can that be consistent? In our models, this qualitative picture, and it needs to be worked out more precisely, but I think it's pretty clear how it's going to work out, is that there is a causal event horizon, and there is also a branchial event horizon. And these are two different, or entanglement event horizon, these are two different horizons. And that essentially what's happening is that the information that the black hole has when it forms is trapped between the entanglement horizon and the causal horizon, and that it is preserved in that zone between the entanglement horizon and the causal horizon for the lifetime of the black hole, and on black hole evaporation just comes back out again. And that is the entanglement horizon. So the causal horizon is a horizon beyond which you don't get to send signals back. The entanglement horizon is the horizon beyond which basically you don't get to make your mind up about what happened. There's no classical way to make your mind up. In other words, at the entanglement horizon, just as you are sort of stretched at, tidal forces stretch you in physical space, so in a sense, you're being stretched at the entanglement horizon to the point where your classical mind sort of can't make its mind up about which quantum thing happened. And so, the sort of the picture is that that there are effects at the causal horizon that are classical effects that sort of can't get out of the causal horizon, but the effects at the entanglement horizon, there are quantum effects that can kind of go through the entanglement horizon, but cannot be classically, they sort of can't classically escape from the entanglement horizon. That's at least a rough way to say it. Jonathan, do you have a crisper way to say that?
No, I think that's basically right. That the sort of the Hawking process is just the leaking out of microstates that correspond to particular, global multiwave states from an entanglement horizon which exists because of the presence of a causal horizon. Yeah, I think that's our current sort of, as you say, the current qualitative picture for how that will work out. But actually,
I started, a couple of months ago, I started exploring specific black holes and doing actual experiments to find different structures of black holes. The main thing I discovered is that black holes are not as simple as you think. Black holes in a model with discrete spacetime and so on have all kinds of interesting effects and their structure is complicated, and you have black holes inside black holes and things like this, which you can also get in general relativity, but it's less clear what's going on. I mean, what's very beautiful in our models is the space-like singularity at the center of a Schwarzschild black hole is just the termination of rewriting rules. So in other words, time ends. Just like if you hit the singularity, if you get inside a Schwarzschild black hole, a non-rotating black hole, you are inexorably led to the singularity. In other words, the future of everybody is to be at the singularity. And you see that absolutely explicitly in our models, because all the paths of the lead of the causal graph just lead to termination. Time stops. It's as if, you're going along and it's like everything dies. Time stops. Nothing happens. So that's so you can kind of see those things, but then you see some additional effects. So one effect I haven't really explored properly is what I was calling the black hole wind, an analogy to the solar wind. So it's a continual momentum transfer outside of the black hole that you could think of as being graviton-Hawking radiation. It's a radiation, it's a quantum radiation, a quantum gravitational radiation. And I don't know whether people have studied that in traditional Hawking radiation. I mean, one would expect graviton radiation, but since gravitons play so badly with standard quantum field theory, I'm not sure that's been properly investigated. But what this is basically a momentum transfer out of the black hole associated with essentially unpaired graviton vacuum fluctuations. And that's an example. So I mean, that would be an example probably of a prediction of our models, which is really an inevitable consequence of discreteness of space-time, I think, but needs to be investigated. Question from Kick. Can this somehow be related to amplituhedron theory? Good question, probably yes. I don't think we know exactly how, and I don't think we need to talk to Nima and friends about more about amplituhedron theory. I think it's been a couple of months since I exchanged email with those folk, and I think, I don't know, Jonathan, any words of wisdom about amplituhedrons?
Okay, yeah. So I don't know, because I don't know that much about quantum field theory. I'm not totally familiar with the physics of how the amplituhedron works, but from a mathematical standpoint, it does seem like it's a relevant kind of structure. So the amplituhedron is a way of computing scattering amplitudes in quantum field theory, particularly in certain types of topological string theories in twistor space, using this structure, which is a positive Grassmannian, which has this representation as an amplituhedron. And the reason the amplituhedron is interesting, that this positive Grassmannian is interesting, is because it's generalizing. Okay, so if you have a projective space, you can construct a simplicial decomposition of that projective space, and so you're doing this topological decomposition into these individual simplices, which are just these simple kind of combinatorial structures. Now, the projective Grassmannian, which is this amplituhedron, is some kind of generalization of the concept of a simplex to sort of arbitrary polytopes that exist in algebraic geometry, and in particular to this particular Grassmannian space that's used in the context of twistor theory. And so it's one possible route to understanding geometrical structures like the causal network, like the multi-way causal network, I should say. Because one way of thinking about, how does a space-time causal network limit to a Lorentzian manifold, or how does a hypergraph limit to a Riemannian manifold? One way to think about that is kind of to flip the problem around and start from a Riemannian manifold or start from a Lorentzian manifold and do one of these simplicial decompositions on it and see what combinatorial structure you get out, and you will get something that looks like a hypergraph or looks like a causal graph. And the fact that this amplituhedron gives you a way of generalizing simplicial decompositions to these more abstract kinds of structures, like twistor spaces and correspondence spaces and so on, tells us that maybe there's something there that will give us insight into what the limiting geometry of things like multi-way causal networks is. But as you say, that has to be worked out in detail.
Well, so I mean, what you're saying basically there is that when we say, you take a picture of a picture of a rabbit or something, you can triangulate, there's a classic, the Stanford bunny is the classic one, where you have this three-dimensional object and you're taking the surface of that three-dimensional object and you're breaking it into lots of little triangles. That's a triangulation of the space. What you're saying is that if you have more abstract spaces, in particular twistor spaces, and you want to do a decomposition of the twistor space into polytopes, generalized polyhedra, you're saying that the amplituhedron is a way to think about that decomposition. I wasn't aware of that version of the amplituhedron story. I mean, I was more aware of the story of the scattering amplitudes, where, I mean, we really need to formulate scattering amplitudes properly in our models, because basically a scattering amplitude has to do with thinking about multiple paths in the multi-way graph and the story of what happens to those multiple paths. See, this is one of these cases where a scattering amplitude, normally in quantum field theory, what is a scattering amplitude? A scattering amplitude is you take two particles at infinity, they come in, they collide, they go out to infinity again. And you ask the question, what is the relationship between the particles coming in from infinity and the particles that go out to infinity? And that relationship is usually described in terms of the S matrix. You basically take all the vector of possible states of the incoming particles, the vector of possible states of the outgoing particles, and you say these are related by the S matrix. So it's a very out at infinity, but with particles. And the question is, can we get a version of this that doesn't require us to know how the particles work? Can we get an analog of that scattering amplitude? Because in quantum field theory, scattering amplitudes are talked about in terms of asymptotic particle states, which, by the way, are a total can of worms to define. And in quantum chromodynamics, for example, QCD theory of quarks and gluons, it has been impossible to define those asymptotic states. They just don't, we don't know what structure they have, because usually in the notion of asymptotic states is when particles are sufficiently far away from each other, they don't interact with each other. Great, that's all good and well and good until you realize that in a proton, the quarks are permanently confined. So you never get quarks to be far enough apart that you can think of them as asymptotic and never interacting. So that's, you know, I think, so we don't really know, and maybe we need to think harder about, is there a version of the scattering amplitude story that does not rely on particles? And I think what you're implying, Jonathan, I don't understand it, is that in terms of this decomposition into polytopes, that somehow there's a version, there's a way of getting something like, but by the way, the amplituhedron is a derivative of sort of the string theory thinking that was a derivative of the old S-matrix theory of strong interactions, which basically said, let us consider this S-matrix. What can we say about the S-matrix? Oh, it has certain properties. It has unitarity. It has analyticity. It has crossing symmetry. Analyticity is that as a function of the parameters, like the momenta of the particles that come in, there's a certain continuity with respect to changes in the momenta. Crossing symmetry is a more complicated thing that has to do with exchanging particles and antiparticles and so on. But these are features of this thing that is the S-matrix, and we can kind of home in on what the S-matrix is by saying the S-matrix is this mathematical object with certain features. And you know, what the analog of that is between this sort of triangulation of a space and so on, I don't know. Maybe Jonathan knows how that works.
Well, yeah. Again, like I say, I don't really know and understand enough of the underlying quantum field theory. But so the geometrical picture of what happens is apparently if you the on-shell scattering processes, you know, they form a tree of possible outcomes that's very much like a multi-way evolution graph, and where the scattering amplitudes are the individual sort of weightings of in that tree, and the geometrical structure of that on-shell scattering tree is essentially a generalization of a convex polytope, which you can think of as in turn as being a generalization of a simplex in some abstract projective space. But because because that positive Grossmanian is then used in the computation of the scattering amplitudes, it's then referred to as this amplituhedron. It's some generalized convex polytope that's used in the computation of scattering.
I think the hedron part of it has to do with the momentum conservation. And I think that has to do with basically to say you've got a bunch of vectors that all sum to zero is the statement that you're inside a polytope of a certain shape.
Right.
So I think that's the and the by on-shellness is just this story that the p squareds, the momentum squareds, are equal to the mass squareds, and that's anyway. Okay, fair enough. Question from Tarka about strong and weak nuclear forces. That's kind of what we're talking about in terms of that. Things are invariant under a local gauge transformation that is SU3 cross SU2 cross U1. And SU3 and SU2 and U1, those are designations of types of Lie groups, essentially symmetry groups of different kinds of things. SU2 is roughly the symmetry group, the rotation group, although it's a little bit more than the rotation group. SU3 is a generalized, well, these are, SU stands for special unitary. That means that it is the set of matrices that have determinant 1 on a unitary matrices, 3x3 unitary matrices with determinant 1 is a way to think about what's in that. It's the group of those things. But I mean, that's an obscure way to say it. That's an obscure mathematical way to say it. But basically, it is generally believed that these three different pieces, the SU3 is the thing that gives you the quark-gluon sector, SU2 cross U1 gives you electromagnetism and the weak forces. But it's generally believed that all those things actually are part of one sort of master group that breaks down into those three separate subgroups. The question is, in our models, if we look at the limit, just as we can look at the limit of a spatial hypergraph and say, what's the limiting space-time? What's the limiting dimension of space or whatever else? What's the limiting Lie group, the limiting continuous group that you get when you have a big enough kind of bag of permutations in our models? And we don't know, and we don't know whether there's particular families of Lie groups that are possible to get. Like, for example, if we could show that everything you get would have to be a subgroup of E8, for example, the exceptional group E8, then that will be a spectacular thing to show, because SU3 cross SU2 cross U1 is a subgroup for SU5, which is a subgroup of SO10, which is a subgroup of E7, which is a subgroup of E8, if I remember my Lie group theory correctly. It's by no means obvious, it's completely unclear, but it could be the case that there's a generic fact that that this structure, this limiting structure, has to be some subgroup of this particular kind of Lie group. I don't know if that's true. If that was the case, it would give us a tremendous boost in terms of thinking about the standard model of particle physics. We don't know if that's right. Questions here about particles and maximum entropy and so on. That's a big can of worms. I mean, entropy, the notion of entropy is the notion of, when you look at a system, how many different microscopic states are consistent with how you describe the system. So if the way you describe the system is to just say, oh, it's a big bucket of nodes and they're roughly arranged to be three-dimensional, so that their average dimension is 3, then that implies a certain entropy, because there's a certain number of microscopic arrangements which are all compatible with that macroscopic statement. How that works in terms of different regions, what entropy you assign depends on what your macroscopic description is. In the language of like Gibbs and people like that, the sort of theoretical statistical mechanics, it's the coarse graining procedure that you use, which determines the effective entropy that you will get. And people have sort of naively just barreled forward with certain assumptions, typically from chemistry, about what the coarse graining procedure, and from practical thermodynamics for engineering, with what the appropriate coarse graining procedures are. It's not clear how those relate to what the sort of theoretical ones could be. Yeah, so it's a complicated story. How many generations will we have to go in the evolution of our models before we start to see particles? We don't know. But in our current estimates, it's really a lot, like 10 to the 80th and things, which is far too many for us to simulate. And we have to hope that there's a way of kind of mathematically jumping ahead. And we've been surprised at how successfully we've been able to do that. Let's see. Question here from Ryan. Why do most modern scientists use math to validate their theories, but claim that math is also man-made? Shouldn't math be fundamental, like a scientist in a video game using code but denying that the code exists? Oh boy, that's a complicated philosophical tangle there. Gosh. And I might be the right person to ask this question of, because I've really thought about a lot of the pieces that go into this. I mean, in our models, it's a model that says you apply these rules, and if you apply them enough times, you get something which is in precise detail what our universe is like. It doesn't say it is our universe, because it's an abstract set of rules. It is a representation of our universe. Now, if you say, if we are entities within that universe operating according to that representation of the universe, how do we think about using the representation to represent the thing that is being represented by that representation? Actually, I don't think is that difficult. It's basically just saying that there's a representation which, okay, the real issue is in our brains, which is what we care about, because that's where we're thinking about stuff. Can we make a bridge between what we can understand in our brains and how the actual universe works? And can we make a representation of how the actual universe works that is accessible to our brains? And that's kind of what the story of actually explicitly creating models is about. Otherwise, just say, why bother to create models? Just say, here's the universe. It just does what it does. Be happy, so to speak. So, I mean, there's probably more to say to unpack this better, but that's my immediate sort of real-time philosophy version of that. Okay, question from J. Lowe here. Is there an interpretation of the speed at which time is ticking? Is it possible that time speeds up with the growth of the hypergraph? Yeah, so in our models, time is the inexorable progress of computation. So time is only, we only perceive time insofar as time in us is going forward. That is, if nothing was changing in our brains, we wouldn't perceive anything as happening. We have to, our brains have to be updated, just like the rest of the universe has to be updated, but our brains have to be updated for us to perceive the changes in the rest of the universe. So time is, in our models, simply this inexorable process of computation by which things are updated. And so psychological time is the updating of things in our brains. Astronomical time is the updating of the structure of the universe, and so on. And all these different arrows of time are necessarily aligned because they're all just about the progress of computation. And this question of is time speeding up is really sort of a meaningless question, because its time is defined by that inexorable process of computation. It's happening in our brains, it's happening in the universe at large. It's sort of happening everywhere at whatever rate you say it's happening, because you could just say, oh, I don't want to consider the next update in the universe. I'm just going to take the universe as it is now and not consider the next one. But the next one will happen in the universe. And if you say, let's see what consequences that had for our brains, you will conclude that the next step of time occurred. So there's no sense, in other words, we're all sort of locked together. Us and the universe are sort of locked together in the perception of how fast time goes. Now, we can have things like we could sort of reach a singularity. We could reach the point where the universe just stops, but we won't perceive that because we will have stopped. And so it's just like, it's the end, you know, game over, so to speak. But it's not like we would ponder, oh my gosh, that's so unfortunate, the game is over. We just stop and there's no more pondering to be done. Everything is finished. I don't think that's the way the universe is going to end, but that is something that can happen in parts of the universe, like inside black holes. So question is, are we worried that our set of tools won't be enough to understand the fundamental nature of reality? Oh yeah, I mean, you know, I don't know whether how far we're going to be able to get, you know, this year, this decade, this century. We don't know. We simply don't know. We've gotten a lot further than I expected. We've gotten further than I thought we'd get in a century. So that's very encouraging. But, you know, it doesn't mean that we don't know how far we'll get, how quickly, and what level of tools will be needed to understand what kinds of things. As I say, it's been going better than expected. That's all I could really say. Question from Mega is, can there be a region of the universe where time runs 100 times faster? You know, I kind of partly answered this, but time is also related to energy in our models. And in a sense, one could say that there is, if you imagine, so, and again, this is, the time running faster is also related to causal graphs and relativity and so on. I mean, that's a complicated mess of a question, in the sense that, you know, just like in a gravitational field, there is the time effectively runs faster. Yeah, it's a complicated question. I mean, I think that, and you have all kinds of twin paradoxes and so on. I mean, the answer is yes, time can run at different speeds in different places, because time is something which is is part of the dynamics of our brains operating, and that dynamics is affected by the overall dynamics of the structure of space and what's happening in the universe at a particular place in the universe. There's a question from Joe. Is particle physics time reversible? Does that imply the rewrite rules for the universe must be symmetric? 2 points. First of all, even if the rules are not symmetrical, on average, after you run them a lot of times, they will behave as if they're roughly symmetrical. If they don't, as soon as you get some kind of equilibrium where there's sort of on average things more or less stay the same, that implies that running it forwards in time and running it backwards in times will look roughly the same. That's the first statement to make. So it's unremarkable that there is approximate time symmetry in the universe. There isn't exact time symmetry in the universe. The universe is expanding, and that generates time asymmetry in all features of the universe if we look at them sufficiently closely. Now, there's another phenomenon in particle physics which is quite separate, or so it appears, from the expansion of the universe. That's the violation of time reversal invariance, or CP violation, charge conjugation parity violation. It's a phenomenon that was discovered in 1964. somewhat surprising phenomenon that was initially observed in the obscure decays of the K0 meson. Obscurely what happens is that the K0 particle, particular kind of short-lived particle, lives about 10 to the minus 8 seconds, 10 to the minus 8, 10 minus 10 seconds. For the K0. It is a particle which decays after 10 to the minus 10 seconds on average into 2 pions, okay, or sometimes 3 pions. But the question of whether this is going into into details of quantum mechanics, but there are, for people who know quantum mechanics, there are 2 eigenstates of the K0 and K0 bar, the K0 particle and the antiparticle of K0. The eigenstates, the quantum eigenstates, are combinations, linear combinations of the particle and the antiparticle. Anyway, blah, 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 long story. But basically what happens is you can see fluctuations between the K0 and the K0 bar in the evolution of such a system, and what you would get going forwards in time, the fluctuations look different from the ones going backwards in time. And so that's a kind of way of seeing time reversal violation, that the universe's microscopic laws are not time reversal invariant. But that doesn't mean that, for example, probability isn't conserved. That's perfectly well conserved. It just means there's a detail of the way the universe works that for which the time is not symmetric. Whether that is connected to the expansion of the universe, nobody knows. I doubt that it is actually. I think it's probably a different phenomenon, but we don't know how that works in our models. We have some vague ideas of how, well, we have some vague ideas, but we don't know in any detail. Let's see, there's a question from Joran here. Is it possible that no tiling pattern creates space? The locality arises purely from the fundamental rule doing some sort of graph simplification. Yeah, that's more or less the story. The space is not in our models any kind of regular grid or tiling. Space is this complicated mess of connections between these points in these graphs, and it is the fact that there is a large scale structure, that on a large scale the graph has certain properties that leads to the fact that space appears to have the kind of simple continuous properties that it does. Okay. There's a question from Winterstorm. How are hypergraphs in our system related to hypergraphs that neural net researchers use or causal studies at the Perimeter Institute? Wow, okay, I think those are 2 really different things. So I'm guessing causal studies is probably causal set theory. And I think Jonathan is, even as we speak, writing a paper about the detailed connections between causal set theory and our models. Causal set theory is kind of a simplified special case of what we're doing. Our models provide kind of a dynamics for causal set theory. Jonathan, do you want to make a more specific comment there?
Not really, no. I think that's pretty much exactly what the correspondence is at a high level. So our model is kind of one way you can think of it is it's an algorithmic procedure for generating causal sets deterministically. So causal set theorists, generally how they've thought about these things is they as we kind of discussed earlier, you start from some space-time, you start from some Lorentzian manifold, and then using something like a Poisson process or some uniform sampling process, you sprinkle space-time events in such a way, and then you define a causal partial order between them that's consistent with the underlying causal partial order of the space-time, and so you get this discrete approximation to the space-time, which is the causal set. And then there has been more recent work relating to these so-called classical sequential growth models developed by people like David Rideout, which attempt to define a dynamics for causal sets by kind of essentially in a stochastic way. And so a few points to make. So one is, yeah, as I said, effectively our approach with causal networks. Basically, if you take a transitive reduction of a causal network, you get a causal set. You get a Hasse diagram for a causal set, and so they are just algorithmic procedures for generating causal sets. These kinds of dynamics that people have considered in causal set theory, like classical sequential growth, they are special cases of multi-way evolution. So for instance, the classical sequential growth model is the model in which there is no isomorphism testing. So you just get divergences in the multi-way evolution graph, and in which at each step a single node is being added. A single space-time event is being added at each step. So if you evolve the multi-way graph of, for such a system, and you assign each path to have a sort of uniform probability, what you recover is exactly the classical sequential growth model of causal set theory. There are also other kind of correspondences which we're also sort of studying. So for instance, this approach to formulating the Einstein field equation, in causal set theory using this thing called the Benincasa-Dowker action, which is kind of the discrete analog of the Einstein-Hilbert action. It turns out that's a special case. So we have a way of formulating the Einstein-Hilbert action, a discrete version of it, that depends only on the assumption that the causal network dynamics are weakly ergodic, that they satisfy basically some molecular chaos assumption. The Benincasa-Dowker action assumes that they are that the causal elements are produced by this Poisson process. So the Poisson process is a particular instance of a weakly ergodic dynamics, but it's not the most general case. In effect, what we have is a significant generalization of the Benincasa-Dowker action in our formulation of the Einstein field equations. So in a few different places, we can see where causal set theory basically gives us certain idealizations to or certain special cases of the things that we've been investigating in the context of our models.
Oh, roughly, one way to say it is, we have a dynamics that actually generates, according to a rule, certain things. In causal set theory, we just say, let's pick at random these things, and those things that are picked at random are roughly something that could be generated by our kind of model. That's I mean, just by fiat, you're saying you pick things at random in causal set theory, but whereas we're saying we actually know how to generate those things. Okay, let's see. The second part of this question was about neural nets and hypergraphs. So usually in neural networks, one is dealing with ordinary graphs. Hypergraphs have not really been a thing yet in neural nets, except that we were just looking at the generalization of our neural net framework in Wolfram language, and actually just starting to look at some hypergraph generalizations of that. So there are the way that graphs arise in neural nets are a little bit different, or it seems that way at least, because neural nets tend to be organized in things like particular layers and so on. It's sort of it appears to be a different story from the things that we're dealing with, at least for the time being. Although maybe there are some analogies between the way that training works in neural networks and the way that multi-way graphs work in our systems, but I don't yet know that. Question from Saints: does the atomization of space provide a solution for the Navier-Stokes equations? No. The Navier-Stokes equations are okay, there are a couple of things to say about this. The Navier-Stokes equations are the equations of fluid flow. And one of the things about fluid flow is fluids are ultimately made of molecules. When people try and solve the Navier-Stokes equations on a computer, they end up having to break down the continuous fluid into discrete pieces and then see how to take limits as those discrete pieces get small. In a real fluid, it's sort of taking that limit physically because it has discrete molecules, and you're just seeing a large number of discrete molecules doing their thing. I mean, I made up this method for doing fluid dynamics back in the mid-1980s that was based on just starting from those discrete molecules, actually very idealized discrete molecules, and then building up to the full Navier-Stokes equations. You can think of our approach to the Einstein equations as being sort of the analog of that, but instead of dealing with these sort of discrete molecules in a fluid, we're just dealing with these sort of discrete atoms of space and so on. And so there's a notion in which what we're saying is we could work up to the Einstein equations from these discrete structures of space-time rather than working down from the Einstein equations and making discrete numerical approximations. Same with the Navier-Stokes equations. Now, the question in the Einstein equations is, what singularities are there in the Einstein equations? What bizarre things can happen in the Einstein equations? And going down from the continuous version of the Einstein equations, people have been able to figure out certain things. We are learning different things going up from the discrete version of the Einstein equations. And so, for example, that faster than light analysis that I did recently is a creature of going up from the discrete end rather than down from the continuous end. Now, in the case of the Navier-Stokes equations, there's a question of what things can you learn going down from the continuous and up from the discrete. Both are difficult, really difficult. So, for example, the big issue with the Navier-Stokes equations is existence in uniqueness. That means, given the Navier-Stokes equations, given these mathematical equations, is there a unique fluid flow consistent with saying the fluid starts in this with this velocity and has this boundary, et cetera, et cetera, et cetera? Is there a unique flow for the fluid consistent with that? Or more bizarrely, does there exist a fluid flow? What on earth does that mean? Well, that could mean you think you can set up the equations with these initial conditions, but after a while, the equations say, sorry, there's no solution. Now, you can say, but look, how could that possibly be right? Because the physics has to do something. The fluid has to do something. What does it mean that the solution doesn't exist? Okay, it's a complicated thing. One of the more amusing cases of that, or amusing, I don't know, but interesting cases of that, when people were trying to first break the sound barrier with planes, there are these bizarre instabilities that happen near the sound barrier. And those can be thought of in terms of the equations people studied at the time as what happened, when the solution to the equations doesn't exist. That's the time when your plane undergoes these huge, instabilities and the thing is almost pulled apart and so on. Or actually was pulled apart, unfortunately, in a bunch of cases when people first tried to do that. But the question of existence and uniqueness for the Navier-Stokes equations, which is sort of a key problem there, is a question of when you go down from this continuous formulation, what do you get to? Sort of those questions don't exist when you go up from the molecular case, but you might, they do exist in the following sense. It could be the case that when you go up from a molecular level, you simply never reach something which can be described in terms of continuum equations. And that's the situation that we're talking about in the Einstein equations and in structure of space-time. It could be the case that there are these bizarre features of space-time which come up from the discrete, and you never really can identify them as being a thing in the continuous space. So an example of that is topology change. If you have something that consists of it's a sphere, and then oops, it turns into a donut with a hole in it. That's not something that can happen in a continuous system, but it can happen in a discrete system. And so there are things like that are possible phenomena that just could exist coming up from the discrete and don't exist going down from the continuous. And there might be phenomena like that exist in the Navier-Stokes equations. I'm not sure. There might be things that are associated with turbulence, which we don't know whether turbulence is a phenomenon of the continuous Navier-Stokes equations, or it's a phenomenon that relies on details of the molecular structure of the fluid to explain why there's all this randomness. I personally think it's probably properties of the continuous equations, although it will be super hard to find there. Actually, I found some toy versions of those equations 25 years ago or something that a student working with us is studying right now that have a bunch of these properties that are a bit like the Navier-Stokes equations in producing really random, complicated stuff, even though they're very simple equations. And even though there is, in the case of those equations, there is no underneath to those equations. There's no molecules that made those equations. They're just mathematical equations that you write down. Let's see, there's a question from Andrew here. In our models, does entanglement have a limit in physical space? Well, let's see. That depends on the relationship between branchial space and physical space and local multi-way systems and so on. And the answer is probably yes. But we don't completely understand how that works yet, I think. And Jonathan has disappeared from video and may have disappeared completely, but he might have an opinion on that subject.
No, sorry, I left for a moment. So basically what that's asking is, I think what this question is asking is the maximum entanglement speed implied by our model, can you ever get to a point where that provides a sufficient impediment that you can no longer entangle two microstates if they are separated by a certain distance in physical space? So just like in cosmology, in ordinary physical space, we have things like the particle horizon, which tell us effectively the outermost limits of the things that we can ever be causally connected with in space-time. I guess the question is asking, is there an analog of the particle horizon but for entanglement?
The answer should be yes.
My reasoning, yeah, and the answer should be yes. It would be much, much larger probably than the cosmological particle horizon, but it will presumably still be finite. How it compares to the actual cosmological size of the universe, that's an interesting question. We don't, and I don't think.
Well, and also in the case of black hole mergers, we don't know the speed of light limits the speed at which black holes can merge, but the maximum entanglement speed also limits the speed at which black holes can merge. And probably for small black holes, the speed of light is a more important limit. For large black holes, it's not so clear. It depends on the scale of the maximum entanglement speed. But what you will see there is an actual physical effect of, entanglement will be the limiting feature of, to get these two black holes together, there will be a limit to how fast the quantum states can be entangled. But we don't yet know the precise dynamics of how that works. There's a question here from Mustafa. When does energy become a particle in the hypergraph? Well, so we have a bulk notion of energy, and the question of how, and you could break down that energy, you could kind of decompose that energy probably into these things that we can think of as being like particles. We don't yet know how to do that. But in general, the sort of bulk presence of energy could be thought of as the sum of lots of microscopic particles that each have a certain contribution to the energy, and that's but if you're asking when does energy become like a particle, that's kind of there is no notion of, well, in standard quantum field theory, all energy is thought of as decomposed into particle excitations. Whether it's a photon that's more sort of pure energy or an electron, whatever. In quantum field theory, one of the ideas is all energy is decomposed into particle modes. Now, I say all energy, and there is a little bit of an exception to that because there are these other solutions like instanton solutions, things like this, that are kind of other so-called non-perturbative solutions to the equations of quantum field theory that are not just like particles. But most of the time in things which we think of are directly connected to experiments, where we're doing scattering experiments and things, we always say we're going to start with particles and end with particles. And so in those cases, the notion that the idea is all energy can be decomposed into particles. That's what I thought we were going to have to understand energy in our models. We actually have a bulk version of energy where we haven't decomposed it yet into particles. But presumably our energy can be decomposed into particles as it can in quantum field theory, except maybe there are cases where it can't be, except maybe there are cases where there are structures that aren't like particles. Like in quantum field theory, there can be things like cosmic strings that aren't really like particles, or ordinary strings that aren't really quite like particles, although they have certain similar features. Other kinds of sort of collective structures that aren't really like particles. We don't know how those work yet in our models.
By the way, I should mention, I have a suspicion that there may be a sort of Ramsey theoretic way of viewing that. That, in other words, when you have a sufficiently large number of causal edges, certain topological obstructions essentially become inevitable. So that if you're only looking at a small bundle, that there is no obvious sort of decomposition into particles. But as soon as you have a sufficiently large ensemble of causal edges, it will naturally decompose into particles, essentially for Ramsey theoretic reasons.
That would be an interesting claim. Let me see if I believe that claim.
I have no idea if it's true. It's a suspicion that I've had.
Well, I mean, so to comment for people about Ramsey theory, the point is that in a sufficiently large graph, for example, there inevitably have to be, just by the nature of the graph, there inevitably have to be certain features that, actually, let's take a simpler example. In any sufficiently long sequence of numbers, you eventually have to have numbers that form an arithmetic progression. I think that's a correct Ramsey theoretic result. And that's to say, well, if you have enough numbers, there's just no choice but to have things that are in arithmetic progression. You're not saying which arithmetic progression, but there exists some arithmetic progression. And there's similar statements about graphs. And what Jonathan is suggesting is that it's an interesting possible idea. It would have to generalize Ramsey theory quite a bit.
Probably, but it would be in the same sort of spirit. That I don't know. It started off with the conjecture about. I was thinking a bit about cosmological baryogenesis and whether there's a Ramsey theoretic way of thinking about that, right? That once the hypergraph reaches a certain size, certain topological features become, certain topological obstructions become inevitable. And I'm also wondering whether there's an equivalent thing about, if you have sufficient energy density, if you have sufficient causal edges, if there's enough hypergraph activity, that again, certain topological features become inevitable. It's a generalization of Ramsey theory in the sense that it's dynamic in a way that Ramsey theory generally isn't, right? So we should
investigate this. This is another thing to put pin on the this, because we can investigate this completely empirically. And that's a good thing to investigate. Yeah, I agree. I mean, in other words, what subgraphs, for instance, are inevitable subgraphs that have to occur? That would be a concrete way to investigate this. We're probably running out of time soon, but let's see. A question from Parmenides about the compactness property of logic. I don't know what the compactness property of logic is. Does Jonathan know?
Yeah, so there's okay, so quick background to why it's called the compactness properties. There are these things called stone spaces, which are these totally disconnected Hausdorff spaces in topology. But crucially they're compact spaces. And it turns out they were studied by this guy Stone for, amongst other reasons, the fact that they turn out to be a natural kind of topological interpretation of Boolean algebras. Boolean algebras have a natural spatial structure, and it turns out it's these stone spaces. There's a theory.
Spatial structures are hypergraphs, right? I mean, it's 2 to the n dimensional hypergraphs, isn't it?
Basically, yes.
I'm sorry, hypercubes. I meant to say hypercubes.
Yes. Yes, right, exactly. Yeah, if you formulate them as a lattice, they form hypercubes. And so then in topology, there's this thing called Tikhonov's theorem that says if you take the product space of a bunch of compact spaces, and that product space is itself compact. So if you apply that to stone spaces corresponding to Boolean algebras, it tells you something about first order logic, and in particular, it tells you that if you have a collection of sentences in first order logic, then that set of sentences will have a model if and only if every subset of those sentences has a model. Which is basically what you're doing is you're taking your stone space, which is compact, and you're looking at the subspaces and showing that those are also compact. In terms of how you interpret that in R formalism, I have a conjectural answer, but it's not very well thought through because I'm literally just thinking about it now. But okay, so
I love the way you say I have a conjectural answer because you thought of it right now. Okay, keep going, please.
Right, because so interpreting these multi-way evolution graphs as being proof graphs. Right. So your multi-way rules correspond basically to axiomatic transformations between symbolic expressions. Each node is a symbolic expression. Every path in the multi-way evolution graph is then a proof of equivalence between some expressions, or a proof of implication between expressions. So then in that instance, we have this sort of conjectural way of formulating models by coordinatizing those proof graphs, effectively by foliating them into a sort of expression-like hypersurfaces, or whatever the appropriate name is. And so each such choice of foliation is a different choice of model. And so essentially if you consider multi-way systems that are produced by first order theories, what the compactness theorem would be telling you is that, so we already know that if you have 2 multi-way systems corresponding to individual rules, you can consider the composite multi-way system, which is like some kind of tensor product of the 2 individual multi-way systems. And so what this would be, and that actually has a natural product topology, which is already quite encouraging. And so what the compactness theorem would basically be saying is that your composite multi-way system is foliatable if and only if all of the sort of constituent multi-way systems are foliatable, which is an interesting thought and not one that I'd really sort of internalized.
Well, so what that would mean is, to be foliatable is to say there exists a model.
Yes, right. And so we exactly. So and we know that there are certain combinatorial properties that have to be satisfied for the system to be foliatable. So one example is there can't exist cycles. If there exist cycles, that's a failure of hyperbolicity in the continuum.
What is the interpretation of cycles in a metamathematical graph?
That is an interesting. Well, I guess that's some kind of tautology, right? That's some circular, some inevitable circular reasoning. I don't know.
Well, it's saying that as you apply the axioms,
basically it's telling you that the deduction relation is not well founded, which is another way of saying that it's circular.
Which is probably to say that almost anything is true in some sense, that you will get back to, why does it, wait a minute. No, there's more to this. If you have something where you apply the axioms, they go through a bunch of different states and then they come back to the same thing again. In the usual interpretation, I think that means that for some reason, I think that means that anything can be considered true, that there's some, that you don't connect to a truth at the top, so to speak, that implies a bunch of things. you're independently, yeah, okay. So, but that's an example. Yeah, we need to understand closed time-like curves in mathematics. So, okay, another thing pinned to the list of things to understand. All right. That was an interesting question, though. Thank you. Confused is asking, in a computational universe, is everything running at the same speed? Is our time just a human perception of the speed of computation in branch-Hill space? Yeah, I mean, yes, time is, everything is, as I was explaining before, I mean, it's like our brains are computing our, and the universe is computing, and the sort of rate of computation, the intrinsic rate of computation can be considered to be the same. You could consider it to be different. You could say our brain didn't update at all, but then we have no perception of what happened in the universe. So you might as well say it's all happening at the same speed. Okay, so let's see. Tori is asking, returning to the neural net theme, adversarial attacks seem to point towards a much different way that neural nets perceive data. You can change a picture just by changing a few pixels and so on. So are we trying to make them think with our prior, but they still do something different? Right, so the question is, how do you confuse a neural net versus how do you confuse a human? You know, we think that the confusion of us humans is less fragile than the confusion of current neural nets, and that's probably true. But that probably is a consequence of some details of the way that current neural nets are trained and so on. I doubt that I mean, you can confuse humans in all sorts of ways. It's like, you know, you ask a person, why were you confused? And in the end, there'll be a very complicated story often of why they were confused. I mean, it's like, why do I think, you know, I glance at something and I think, oh, there's an eagle in that tree, but actually it isn't an eagle. Actually, it's a pattern of leaves. And it's like, well, why was I confused? And, you know, it's complicated. And I don't think that my story of confusion is necessarily any more embarrassing, so to speak, than the story of confusion, or less embarrassing than the story of confusion of a neural net. So I don't think there's a fundamental difference there. I'm not sure, but I don't think there is. And I think that the notion, I mean, the common thing with humans is we get to use common sense from other places to think about things, whereas our neural nets tend to be, you know, one-trick ponies, so to speak, that are just doing one thing and don't get to, you know, if the neural net concluded that is a picture of a crocodile riding a bicycle, right, based on its way of understanding how things worked, and you say, but crocodiles don't ride bicycles. That's just not the way bicycles are set up. But that's a piece of knowledge that in principle could be part of what the neural net knows, but isn't what the one-trick pony of an image identification neural net is supposed to do. Richard here is asking, given a rule set that exhibits universal computation where may nest Wolfram model inside itself, might we discover such meta-interpreters in the natural universe? What would this imply? Yeah, I think such meta-interpreters exist all over the natural universe. I think universal computation is ubiquitous in the natural world. And what that implies is tons of computational equivalence. That is, we look at something and we say, we're very smart. We can figure out what this thing does. But no, that's not the case, because it is as sophisticated as a computer as our brains are. And so when we look at this thing, it's like it's just equivalent to what our brains are doing. So we don't get to figure out what it does any more than because it's just running a computation that's equivalent to what we can do in our brains. So I think that's the sense in which the existence of embedded universal computers embedded within the universal computer, that's the story of what cannot be predicted, is things that for which brains aren't out ahead, brains being an example of a universal computer, but lots of other things also being examples of that. Question from Nodarico. What has been the most interesting or valid disagreement regarding our work from other physicists? Oh boy. You know, the most interesting thing is that a bunch of physicists I know who are good physicists have been seriously trying to understand what we're doing, and they have a hard time because they have a certain way of thinking about things, and this is different. And, you know, I think we are realizing that, you know, these bridges like the one that Jonathan is working on right now to causal set theory are we probably have to build a lot of these bridges. Now, a bunch of people, particularly younger physicists who are working on our models, they've learnt the stack of knowledge that we have in our models and that relate to our models, and that's allowed them to contribute there. And I'm afraid I've been a little disappointed, actually, that people have been less interested in making connections to all these other wonderful areas of physics. Because well, we're making a lot of progress on these models. Let's just keep going. Why should we worry about how these relate to string theory? We don't need string theory right now, which I think is a shame, because I think it's actually not true. I think string theory has gotten a lot to say that will be very useful to us and vice versa. But in terms of I don't know. I mean, there have been people, some number of people don't understand how Lorentz invariance works in our models. And I'm confused by, this is something that I accuse Jonathan of saying, I'm confused why you're confused. This is, but to be fair, anytime when people, try hard and they're still confused, it's a, look, I've spent my life producing, software and computational languages and so on. And, to me, I take user confusion personally, so to speak. In other words, if a user of our system is confused, then it isn't the user's problem, it's my problem, so to speak. And then we didn't explain it properly, or it's badly designed, or whatever else. And I think to some extent, we still need to do more work to really explain, in a way that is unconfusable, so to speak, how some of this stuff works. And one of the issues is, so, we can explain it at an intuitive level, works well. We can explain it at a mathematical level, works well. The mathematical level is kind of sophisticated in some ways. And the question is, at what level, by what vector do you want to understand something? And that's a challenge for different people, because different people have different, I mean, for me, I like to break things down in terms of things that are, for me, simple. But, for me, simple, if it involves some random factoid of quantum field theory that I happened to learn when I was 12 years old, for me, that seems simple. But that's not necessarily simple for somebody else. And so, I think it's a question of how do we make these bridges to the different places? But I don't think, at this point, I don't think we've encountered any, this is a terrible thing to say, but I don't think we've encountered any interesting sort of, oh, how can this possibly be true type thing. Am I mistaking something, Jonathan? I mean, we've encountered, I don't understand this. It's like I don't understand it. Put it in my context type thing. But I don't think we've encountered.
Well, so you mentioned the Lorentz invariance thing, which I think is actually a good example, because so I had this long exchange sort of a little while ago, and it's just restarted again with a fairly famous physicist who I won't name in case they don't want to be named, but who was particularly interested in how we get around this problem of Lorentz invariance. And
so we get around a problem of Lorentz invariance. She thinks that we have at least I assume she thinks that we have that a model of our general type couldn't possibly have Lorentz invariance.
Well, it's a good point, right? That in some sense that it's very counterintuitive. Well, at least it's counterintuitive to me. The idea that you can have a discrete model that is compatible with a continuous symmetry group, right? The Lorentz group is a continuous group. And so I think most people have come to this with the geometrical intuition that a discrete space can't be invariant under a continuous group.
But that's ridiculous, because if you just have a grid, right? The limit of a grid is invariant, at least a randomized, a random walk, a discrete random walk is invariant under rotations.
Right. A grid is a good example of something that is not invariant under rotations, right? Because that's
fair enough.
Grid is something where you can pick out a preferred direction. And
right,
so for
a random walk, you cannot.
Right. But so in causal set theory, the way people deal with this is that there's this actually quite elegant measure theoretic argument that's due to Bombelli, which works by saying you can't define an equivariant measurable map which would be used to pick out a preferred frame, because essentially because the hyperboloid of your unit future directed time like null vectors is a non-compact manifold. And so if you could pick out a preferred frame, you could basically use it to make your measures arbitrarily large. which would violate the axioms of a probability space. Whereas in Euclidean space, you can pick out a preferred frame because the associated the space of unit vectors in Euclidean space is like, is Sn or Sn minus 1, strictly speaking, which is a compact space, and therefore that argument doesn't hold. But in our setup with causal invariance, actually, there's a subtle difference, and actually, this is related to the thing I'm currently writing up for this causal set paper, is exactly how this argument changes in our setup. So, causal invariance, the statement that the causal network is always the same, is always isomorphic for different updating orders. The different choices of updating orders correspond exactly to different correspond exactly to the conformal transformations of spacetime. So the transformations between different reference frames correspond exactly to the actions of the conformal group. And so because both the Lorentz and Poincare groups are subgroups of the conformal group, causal invariance necessarily implies Lorentz invariance in the continuum limit as a corollary. But the place where I thought this particular discussion was interesting was because the physicist I was talking to sort of accepted all of that, but was saying, nevertheless, it has to be the case that the out degree of your individual updating events in the causal network has to be infinite. And again, if you follow through the argument naively, that does in fact seem to be the case. Again, because of the non-compact nature of this hyperboloid, and because all of your future events lie in between the future light cone and the hyperboloid, it appears as though the number of events immediately in the future has to be infinite. So the out degree has to be infinity. The subtlety there, okay, there are several problems with that. One of which is assuming particular features of the distribution, which in fact we don't assume. But actually, even if you assumed something like a Poisson distribution, it's still not quite right, because you're assuming that the individual causal edges are actually observable quantities.
Yeah, you're toast. Once you have a Poisson distribution, you've just determined your space-time basically by saying what the measure of the Poisson distribution, Poisson process is.
Right. But even in that case, it's still recoverable. And this is again one of the things I'm trying to write up.
I'm surprised it's recoverable in that case, but okay.
Well, it's recoverable as long as you basically impose a cutoff on your boosts. If you say I'm allowed to boost up to like 0.99c, then what you can do is say, because our causal edges are so much smaller than anything that can even in principle be observed, what you basically is applying an effective theory in which, so actually I can just quickly share the draft of the paper. You can define this effective theory. So here's your causal network, but this is not itself actually observable. The things you're observing are big blocks of updating events and big blocks of causal edges. So you're basically defining an equivalence relation, which is shown here. So we're partitioning this causal network into equivalence classes that are here shown in red, yellow, purple, etc. So the effective causal network you're seeing is this. And so of course, by making those equivalence classes arbitrarily large, you can force the out degrees of the vertices to be arbitrarily large. And so effectively, as long as you're okay with the idea that you're enforcing a cutoff on the maximum boost, the space you end up with is still causal invariant, and that's a kind of a subtlety that I probably wouldn't have picked up on unless I'd had this particular exchange with this particular physicist. So I think that's at least one example of something which helped clarify my own thinking about this.
Oh yeah, I mean, look, for me, for us, like these discussions and you guys asking these questions on this live stream, this is highly useful. If you hopefully we're providing something interesting for you guys, but you are providing something very useful for us. Even if all you do is ask questions and don't make any suggestions, it's still super useful. Because but by the way, I think the thing that I'm realizing is that a big part of what these guys probably don't understand is the role of essentially molecular chaos in the construction of space-time. They're still imagining that it's some kind of grid type thing. But yeah, we gotta get some more. I mean, there are a number of people, and I feel bad about it because it's like they're really making an effort to understand, and they're running into various problems, like which include problems where I couldn't even see that the problem was there, because it's like just my way of thinking about things is such that it's just I can't see why there's a problem, and this is but I'm trying to avoid Jonathan's I'm confused about how you can be confused. Okay. Richard is saying I better work quicker on the VR Wolfram model stuff I'm working on. Please work on the VR stuff. I really want to see this stuff in virtual reality, and we can get you the stuff that that Max has been doing. I was showing earlier with those animations. That's those animations come. They are minutes of CPU time to generate. They are not the real-time Spring stuff, which we have pieces of, and hopefully we have some code which we're happy to share, which has sort of pieces of implementing that in Unity and so on. Does the model, Stephen is asking, does the model describe absorption emission spectral lines? Well, yes, eventually. I mean, it describes the features of quantum mechanics that will lead to absorption and emission lines, although it doesn't directly deal with those yet. I think we're running out of time, so I'm just going to skip forwards here and look at other things here. There's a question here from David about particular explanation for the Pioneer anomaly, and I have no comment on that because I don't know what that explanation is. And I'm also not even sure what the status of the Pioneer anomaly actually is these days. I'd have to look that up. I thought I had heard things about how, oh no, actually it's all been explained, but I don't know. So I have nothing to say about that. Question from Jason here. Do we lose our reference frame inside a black hole? Oh boy, that's a complicated mess. How to describe that? I mean, when you go into a black hole, the whole structure of space-time is changed. So it's not, there isn't really a, there are reference frames you can make, but they're incompatible with the ones that we currently have. And that's the one way of understanding what an event horizon is.
And we should mention, by the way, that black hole singularities are an example of a failure of global hyperbolicity of space-time. So, around a singularity is a point where if you attempted to foliate your space-time, the universal time function that you're defining would have level surfaces that all kind of stack up around the singularity. And since one of the basically the definition of global hyperbolicity of space-time is that the level surfaces are non-intersecting, a singularity is an isolatable point where you cannot foliate, and in which therefore a reference frame doesn't strictly exist.
Okay, I mean, the definition that you're making of a reference frame is something where you have a reference frame is something where you can sit there and time passes and things happen in the world. Is that and so you're saying at a singularity, time doesn't pass.
Yeah, pretty much, right? So yeah, so a formal definition of what a reference frame is it's a rule for assigning points in space-time to have global time values, and so then the space-like hypersurfaces are the level surfaces of that function.
Right.
But yeah, exactly for this reason, because time doesn't extend, because singularity is a point where your time-like vectors become your time-like paths become future inextendable. That's a point where it's not possible to construct that function because the level surfaces necessarily intersect around that singularity.
There's a question here. Let's see, from Matt. Are points on the hypergraph actual points that are connected via hyperedges, or the points just the place at which the hyperedges diverge and converge? I mean, these things are just a representation of what's going on. So in the way we're usually setting it up, the points in the hypergraph are actual points that are connected by hyperedges, but there is a different view of what's going on where you start from the causal graph and you slice it, and then you have a dual of that. There are a bunch of different interpretations, but at least in the most direct interpretation, there are atoms of space and they are connected by hyperedges. But that's not the only possible interpretation of what's going on. From Christian here, what drives the computation process that we perceive as time? Well, you can be very paradoxical about this, and you could say nothing drives it, but insofar as it happens, therefore we perceive it and we perceive time to have happened. But from the outside, the kind of the external view of the universe, which we don't believe we could ever get, but if we could get an external view of the universe, somebody could say, wait a minute, they waited a century to do that next update. And, you know, how can they, you know, but we wouldn't know that because we're embedded in this universe. And so all we know is that the update happened. So it's not a question of when did the update happen? It's just a question, did it happen? Because the progress of time is defined by these updates happening. And so there is no notion of the speed at which that happens. And that's no notion in a sense of driving that computation process, because if it doesn't happen, then nothing happens. And we don't know nothing happens because we don't know anything, because our process of perception is tied into something happening. Have we used have you used machine learning for making progress and understanding things? I used machine learning a bunch for doing automated, I was looking for particular features of rules for these models and doing sort of visual inspection of large numbers of rules. And I used machine learning to filter that visual inspection. So that's a place where we have used it. I don't think we've used it for anything. Oh yeah, I mean, we were thinking of using it for basically lemma selection, for trying to find paths in these theorem proving things. But I think we may have a better scheme that Jonathan's come up with that is a physics-based scheme for doing that, that won't be a machine learning-based idea. Question from Martian: is traveling through branchial space like traveling through a wormhole? Not really. A wormhole is a different. A wormhole is a connection between two things where space is like, oh, it's like a grid or something, but then there's just this one sort of space tunnel. There's this one extra thread that connects one part of the grid to another part of the grid. That's more like a wormhole. I actually talked about this a bunch in the post that I wrote recently about faster than light, about things going faster than light. I tried to talk about how wormholes relate and so on.
By the way, I think you may be being a little overly dismissive of that question. I mean, that question is basically asking whether ER equals EPR is true, right? Because you know, a wormhole is is a shortcut through a causal network. Is a piece of the causal network that's not part of the continuum Lorentzian structure. A quantum entanglement is essentially a shortcut through branchial space. It's a part through branchial space that's not part of the continuum geometrical structure. And ER equals EPR is sort of conjecturally making the claim that the two things are related. And I think that's kind of what this question is.
Okay, that's okay. I'm sorry, I jumped too quickly there, and you might be, but let me just challenge the point about an entanglement being a non. I mean, in what sense the structure of branchial space is determined by micro entanglements? So in what sense?
In the same way that you can think of space, the structure of space-time is being determined by micro.
Right. Okay. So you're saying a long-range entanglement is like a wormhole. That's a good point, actually. That's a very good point. So you're saying a wormhole in space is like a long-range entanglement in branchial space.
Right. Exactly. So in both cases, they're features that you've engineered in order to ensure greater correlation between 2 points than would otherwise have happened naturally. It's just that one is using the structure of the causal network and one is using the structure of branchial space.
Actually, that's a really interesting way to think about the ER equals EPR story. It's basically to say that there exists the presence of non-local kind of non-standard spatial connections. How is that related to the presence of non-local, non-standard branchial connections? And is that the case? Okay, that's actually a really good formulation. So let me think about that for a second. Is it the case that inevitably in the multi-way causal graph that those two things are related? I bet it is. I bet it is. I bet that I'm sure that that's something we could probably prove. Okay, thank you to Martian there. This is what I like about live stream stuff. Okay, and my mistake for having taken that at the wrong level. Okay, Christian is asking, since brains are part of the universe, shouldn't artificial intelligence be possible to model using the same structures? Yes, but remember, it's happening at a very different level. Yes, I mean, absolutely. Artificial intelligence is a story of computation. Everything we're dealing with is a story of computation. Whether the things, I mean, the big deal of artificial intelligence is not that we get computation. That's easy to get. the big deal of artificial intelligence is, can we get computation that aligns with the human things that we care about, with deciding that's a picture of a cat or a dog, those kinds of things. And that's the question of that's really a question of, is the universe expected to be comprehensible? That is, AI, okay, so this is an interesting circular question. So the statement AI connects to computation is, AI is the human understandable analog, piece of computation in a sense. The universe just does its thing. And the question is the universe expected to be connected to something human understandable? Is it expected to be an AI-like computation, or merely a random computation out there in the universe of all possible computations? Okay, so here's where it gets circular. We exist in the universe. We succeed in operating in the universe. Maybe our way of being constructed is one which has the feature that inevitably the universe seems comprehensible to us, otherwise we wouldn't be able to operate. In other words, the fact that there is coherence to physical laws is a consequence not so much of how the universe operates, but how we are constructed. That there are versions of us that could not conclude that there are coherent physical laws, but we wouldn't have a very interesting time in the universe. And so the very fact that we sort of exist in the universe and can have all the discussions that we're having is a consequence that we happen to be things that exist in the universe in a way for which the universe is comprehensible. So in that sense, maybe there is a connection between sort of the AI as a comprehensible computation and the universe as a comprehensible computation, comprehensible to us, because we are things constructed to make the universe comprehensible, so to speak. So that's a possible connection there. And we have to go real soon here, but Saint asks, what do we think of Roger Penrose's idea of cyclic universes? I don't really have anything particularly to say about that. I mean, I think that Roger has various ideas about entropy in the universe, which I'm not sure, I don't know, quite a lot of, when we're talking about twistor spaces, that's a Roger Penrose production. Twistor spaces are a whole Roger Penrose production. A lot of kind of, Roger Penrose has thought for many, many years about sort of discreteness in space-time with rather different foundations from the ones that we're using, but I suspect that what he has can be thought of as some kind of effective model in some limit of what we're talking about. The cyclic universe idea, I think, is very much driven by ideas about entropy and gravitational entropy and those kinds of things, which I don't know how they relate to what we're dealing with. Jonathan, you want to comment on that?
Yeah, okay. So, I mean, let me just quickly give a sort of my summary of how of Roger's what's called CCC, conformal cyclic cosmology, which my conjecture is it'll ultimately be related to some infinite future versus infinite past limit of the causal network actually being the same. So basically, so how CCC works is you say, okay, in the infinite future of cosmology, where everything's coalesced into black holes and then all the black holes have evaporated, so in effect you just have photons left, then you only have null rays in your space-time. And null rays don't have any notion of time, right? They lie only on the boundaries of light cones, and so so in such a universe, in the infinite future, there's no way of consistently defining a time function. And if there's no way of consistently defining a time function, there's no way of consistently defining a distance either. So in effect, you lose all information about space-time volumes, which means you lose 1/10 of the metric information. So the remaining 9/10 of the metric are associated with the causal structure, which is the conformally invariant structure of space-time. That still remains. That's the thing that's determined by the light rays. So Roger's idea was that's very similar to what happens in the very early universe, where energies are so high that, again, you basically lose 1/10 of the metric and you only care about causal structure. And so his argument is, well, given that these two limits are the same, you can do a conformal rescaling of the infinite future and you get something that looks identical to the infinite past. And so because the causal graphs that we're plotting are exactly a plot of the conformal structure of space-time, Penrose's idea would basically be some statement about how there's an effective theory of the infinite time future of the causal network, which makes it look like the infinite past theory of the causal network, I think.
I hate to admit it, but I last heard Roger Penrose talk about this theory in either 1975 or 1976. And the description that you've given of it is definitely more advanced than the description he gave at that time. So good for him. But I'm a little embarrassed because I realize I am a solid, 45 years out of date or something on this theory. Okay, because at that time it was all talked about in terms of the conformal flatness of the Weyl tensor and arguments about gravitational entropy and so on. Okay, that's a much cleaner version. The one that
there's a way of formulating it in terms of Weyl curvature and things, but yeah.
Okay, but he cleaned it up. He cleaned it up a lot from okay, but in any case, but this idea that in the future it's all photons and they have no notion of time, that's a very bizarre idea. I mean, the claim would be that in the future, wow, that's a bizarre idea. Why does he think that the photons aren't going to condense again into something else? Why does he think that the photon-photon interactions won't eventually lead to, proton-antiproton pairs, which will eventually get separated, which will eventually lead to stars and things again?
Well, I assume if you have infinite expansion, eventually, every photon is contained in its own little cosmological horizon.
If you have infinite expansion, but that assumes that, rapid acceleration of the expansion, right? Which you don't have. In a photon-dominated universe, it just does its thing. It's like it's like FRW, but just with a radiation-dominated universe, right? Which is nothing special.
Right. Yeah, I agree. I don't really know. I'm not even. Every time I've heard Roger speak about it or seen him write about it, he always sort of broaches the idea with a certain amount of embarrassment, which makes me think that I'm not even sure that he necessarily believes it's true. I think he's postulated it as
well, it's like the claim that there's a heat death to the universe, which I now don't believe, because the heat death to the universe is just saying the features of the universe that we think about are not don't seem to be interesting. But there are other features, the microscopic details of where all those photons are going and so on. That has a lot of information in it. It's just one information that right now we are saying, forget it, we don't care about that. I think that but your statement about the the fact that at the beginning of the universe, the causal graph of the beginning of the universe and what you're saying is nothing much happens late in the universe, but also we perceive our perception apparatus also is running very slowly, and therefore the kind of and so we don't notice. In the beginning of the universe, a lot happened in the first 10 to the minus 10 seconds of the universe, but the causal graph has lots of stuff going on. And if we were brains in that first 10 to the minus 10 seconds, we would perceive lots to have happened. But 10 to the 100 years after the beginning of the universe, it's all just photons, but we're just photons too. And so we don't perceive, we are as much perceiving that things are happening as we ever did. I mean, this somewhat reminds me of my longtime friend, John Mazouris, who happened to be a graduate student got his PhD with Roger Penrose long ago, although mostly he's been in the semiconductor industry since. But he has this bizarre theory of I think the funny version of it is the creatures of light theory. That basically, intelligences, you can have intelligences that operate in photons. I hadn't really realized, I'm not sure he's thought about this infinite future version of eventually the universe is all just photons. And then the question is, can you sort of operate, can you operate an intelligence just in photons? The answer is obviously yes. I mean, this is a feature of computational equivalence that is sort of, the answer is obviously yes. And then the question is, in that future, I had not thought about that. That's a very interesting case of my kind of physics of alien intelligences, is what does the universe look like if your brain is made of photons? Good question. Another thing to pin to our list of things to think about. Okay, that's where everything is conformal invariant. Let's see. A question from Loke. Do you think the space-war possible Turing machines that produce some universe could be reduced to some finite set of Turing machines? Well, that's sort of the story of universal computation. And in fact, back 12 years ago, we found the very simplest possible universal Turing machine. And that one universal Turing machine, tiny little thing, can be programmed to do what any other Turing machine can do. So in that sense, yes, you can sort of pull everything back to that one case. Question from NA here. Opinion on DNA computing. Let's not do that here. We can do that another time. That's a story of, I mean, more relevant to us is quantum computing, which is more directly related to our models, and which we do have a bunch of stuff to say about. The question from Bob here: has the model predicted the Dirac equation yet? No, but we really need to do that. That's a story of spinors and fermions and so on, and we really should be able to do that. I think we should be able to get the Dirac equation, but we haven't got it yet. Admiral is asking, time-like curves. Okay, so this is a reference to some paper that I certainly know nothing about. Logic of quantum mechanics derived from classical general relativity. I don't know about this. I mean, that's a Jonathan. Jonathan and other folks look at these kinds of papers all the time. I
hadn't actually seen this one before, and having only read I don't know anything about it. I've only read the abstract, but it does seem somewhat relevant because what it seems to be doing is so. It's known that Boolean algebras can be made to form these structures called orthomodular lattices, and quantum logics can basically, if you weaken some distributivity conditions over the Boolean algebras, you get sort of quantum logics, and we actually make some use of that in the analysis that I did, at least of multi-way evolution graphs. One way you can reconstruct aspects of quantum mechanics is by treating the multi-way evolution graph as being an orthomodular lattice, which you can do as long as it satisfies certain strong causal invariance conditions. And what this paper seems to be talking about is kind of formulating a theory of relativity over these orthomodular lattices, or possibly the other way around.
I was just disappointed flipping through it. I thought it was going to get into a big, complicated development, but it's actually very short, and it just ended, which just looked like it was getting interesting here. But yes, it seems to be a description of kind of a coarse-grained logic of general relativity.
Right, right. Which is basically what we're trying to do with this study of multi-way causal graphs.
Well, good paper to put on our collection of possibly related things. We're trying to have on the website, we're sort of collecting all possible things that we think might be seriously related. Yeah, this is right. So we have a final comment here from Richard saying, in this Penrose picture, the photons may decay and you'd end up with the universe consisting only of neutrinos and antineutrinos. That, I think, is old news, because it used to be thought that neutrinos were massless. Nowadays, we kind of think that neutrinos do have some small mass. So in that, boy, I don't know. I mean, the long future of the universe, what is the universe going to be made of in the end? Very good question. Why do we think, I mean, is it, there are processes, there's something called the Urca process, which is gamma, photon goes to neutrino, antineutrino. It's a process that might happen in some stars. And it's in quantum, in a standard model, it would be a box diagram, Feynman diagram with a virtual box in it. But it would be, is the future of the universe, when everything has decayed, is it all photons? Does it have neutrinos? What happens? I mean, I think there's one of these things where the limit of the limit of the limit, I don't know, I haven't thought about this. It's the, what is it called? Eschatology. Is that the right pronunciation? I don't remember that. What's the right pronunciation of the end of things, the study of the end of things?
Yeah, eschatology.
Eschatology. Okay. Right. The
as in inaugurated versus uninaugurated eschatology.
What's that?
In philosophy, there's some distinction between inaugurated and, particularly in theology, there's a distinction between inaugurated and uninaugurated eschatology.
What does that mean?
Which is about whether you find out only about what happens at the end when you die, or whether it's possible to find out sooner, is the fundamental distinction. So that there's a school of thought that just says, wait and see, and that's how you find out what happens. and then there's the inaugurated I think it's the inaugurated eschatology of the people who think that it's possible to know, to figure out what's going to happen at the end, even before.
You know, the sad thing about all of this is that, in a sense, you know, brains operate and we think about stuff, and then brains stop operating, and that stopping operating of, you know, is very much like space-like singularities. It's very much like it's an end of time type thing. And it's kind of interesting to notice that, you know, when we think about, I mean, in a different situation, you know, when you're falling into a black hole, different scenario, then you get to see the whole future of the universe happen. And so in a sense that would be your I don't know whether it's in inaugurated you know, eschatology is, you know, you're falling into a black hole. It's you're kind of toast, but at least you get to see the whole future of the universe, and you get to answer these questions like, you know, does it end with a bunch of photons and so on, presumably. Anyway, all right, I think it's time to, with that, it's time to wrap up here. And it's a comment actually from Richard about algebras of graph rewriting by Nicolas Behr. We don't know about this. It seems like that's something we should go look up.
I think we did add this to our external references, I believe.
Okay.
We definitely got some stuff by Behr. He's done some relevant things.
Okay, well, listen, we should wrap up here. Thanks for joining us, and look forward to chatting about more things in future. And we are rushing to try and actually write down some of the things that we were talking about here, so that they'll be more coherent and more readable. And look forward to another time. All right, see you later.